A passing black hole could, in theory, yank Earth out of its orbit or even pull chunks of our planet apart. That's how powerful its gravity can be. Before you picture a cartoon vacuum cleaner sucking up your city, let's keep it simple. A black hole is just a spot in space where gravity is insanely strong, like a super heavy bowling ball sitting on a stretched sheet. Anything too close rolls toward it. In the next few minutes you'll learn how close one would have to get to cause real damage, what warning signs we'd actually see in the sky, and whether life would stand a chance, all explained with everyday examples and a little humor. You'll leave knowing the difference between sci-fi panic and real danger, why astronomers aren't losing sleep, and what, if anything, you should worry about. No PhD required. What is a black hole? A black hole is a place in space where gravity is so strong that anything that gets too close cannot get away. Light itself can be pulled in, which is why we call it black. There is no light coming back out. Ordinary gravity, like what keeps you on the ground, becomes extreme near a black hole because a lot of mass has been packed into a very small region. Think of squeezing a giant ball of matter down until it becomes tiny. The pull near that tiny object becomes enormous. Around a black hole there is a boundary often called the event horizon. Cross that boundary and escape becomes impossible, even for light. A useful comparison is a fast-moving river meeting a waterfall. Once you drift past the line where the current pulls you downstream, paddling back is pointless. The event horizon is that invisible line in space where you reach the cosmic point of no return. Scientists still use this simple picture to explain a tricky idea, and you can picture the edge as a last chance sign saying, "Turn back now." At the very center of a black hole, our current theories say all the mass is concentrated in an extremely small region, and the familiar rules of physics stop behaving the way they do elsewhere. This central point is often described as a singularity, which is a technical word that basically means, we don't have a good description yet. It's like reaching the inside of a blender with a broken dial. The instruments we trust don't tell us clearly what's happening in there. So physicists admit they're puzzled and keep working. That's science, and it's a little humbling. Black holes come in different sizes. Some are relatively small, with gravity that dominates only very close to them, while others are enormously massive and sit at the centers of galaxies, influencing stars across vast distances. Size here is tied to how much mass is packed in. A more massive hole has a larger sphere of influence. Picture a small drain in your sink versus a huge whirlpool in a bathtub. Both pull things in, but the scale of their reach is very different. Even though black holes themselves are invisible, we can detect them by watching how they affect nearby things. Gas spiraling in heats up and glows, stars can move in odd orbits, and sometimes we catch very faint ripples in space that tell us two massive objects merged. Observing these signs is a bit like spotting a hidden whirlpool by the way leaves and twigs circle around it. And yes, while black holes sound dramatic and a bit like cosmic vacuum cleaners, they don't go around gobbling up everything in sight. They mostly influence their immediate neighborhood. Black hole sizes, stellar to supermassive. Some black holes weigh only a few times more than our Sun, while others outweigh millions or even billions of suns. Stellar black holes come from massive stars that run out of fuel and collapse under their own weight. It's like a giant building suddenly losing its supports and crumpling into a much smaller footprint. You can think of that collapse as taking something the size of a ballpark and squashing its mass down into a city block. The result is tiny in size compared with a star but enormously heavy for its volume. In everyday terms, imagine fitting the weight of an elephant into the size of a ping-pong ball. Extreme, and a little absurd, but it gets the idea across. A stellar black hole's point of no return is often only a few kilometers across, roughly the size of a small city, depending on its mass. That means the region where nothing can escape is compact, so close to it the gravity is incredibly strong. Far away, however, its pull is just the same as any other object of equal mass would be. Picture a vacuum cleaner. Right next to the nozzle it grabs things fast, but stand a few rooms away and you won't get sucked in. That everyday image helps show why distance matters as much as size. At the other extreme are supermassive black holes seated in the centers of galaxies. They can be millions to billions of times the Sun's mass. These giants can have a boundary that stretches as far as the orbits of planets in a solar system, so their reach is vast. They didn't just pop into existence fully grown, either. They grew by merging with other black holes and swallowing gas and stars, slowly becoming the heavyweights that can steer the motion of entire neighborhoods of stars. Think of them as the gravity version of a city planner. Their presence shapes traffic and layout on a galactic scale. Astronomers also look for middleweights, intermediate mass black holes, that are heavier than stellar ones but much lighter than supermassive. Evidence for these is growing, like finding a few medium-sized rocks between pebbles and boulders while walking on a beach. They may live in star clusters or small galaxies and act as stepping stones in the growth from small to giant black holes, though scientists are still filling in the details. Mass is the key factor in how a black hole behaves, not just its literal size. A small black hole sitting very near Earth would tug on us more than a supermassive one sitting very far away. To use a simple life example, a compact car parked next to you feels heavier to push than a heavy truck parked across the street. Also, interestingly, the average density inside the boundary of a black hole can get lower as the mass grows, so supermassive ones can be huge yet, in a sense, spread out, while small ones are extremely compact. Strange, but true. We detect these different sizes by watching how nearby gas and stars move and glow, or by catching bright flashes when something falls in. Observations of stars orbiting an invisible, massive center in our galaxy point to a supermassive object there, and bright, swirling gas near smaller black holes betrays the presence of stellar ones. That's how astronomers tell the petite from the massive, not by looking directly at them, but by watching how the neighborhood behaves when one shows up. Anatomy of a black hole, event horizon and singularity. At the event horizon you reach a point where escaping becomes physically impossible because the speed needed to get away equals the speed of light. Escape velocity is just a scientific way of saying how fast you must move to break free from gravity. On Earth you can throw a ball and it falls back, but near that boundary you would need to zip away at light speed, which nothing with mass can do. Calling it a point of no return is accurate without being dramatic. Once anything, matter, light, or your worst decisions, crosses that line, information cannot get back out to the outside universe. Picture the event horizon as a one-way door. It's not a wall you hit, but a boundary in spacetime that shuts off the exit sign. The event horizon is not a solid surface you could touch. Instead, it's more like the edge of a waterfall in how it acts. Water smoothly flows across the lip and becomes part of the fall without hitting a physical ledge. No bump, no doorbell, just a change in how spacetime behaves. Close to that edge clocks, as seen from far away, slow down dramatically. That means a person falling in would seem to slow and fade to an outside observer, while the falling person experiences time normally. It's a relativity trick rather than a theater illusion, though it can feel like watching someone stuck in a slow-motion scene from a movie. At the very center, models of gravity predict a singularity, a region where the usual laws of physics break down and quantities like curvature become extremely large. Saying singularity doesn't mean a literal point we understand, it signals that our current equations are pushed beyond their reliable limits. You can think of it like crumpling a map until all the roads overlap. The map no longer tells you useful directions at that one tiny crushed spot. Scientists expect that a more complete theory, combining quantum ideas with gravity, would describe what actually happens instead of an infinitely sharp point. Tidal forces connect the horizon and the singularity in a very practical way. They stretch and squeeze objects that fall in. These forces arise because gravity is stronger on the side of an object closer to the center than on the far side, and the difference pulls things apart. For small black holes the stretching is extreme and you would be pulled apart, a process nicknamed spaghettification, long before you noticed any scenic views. For very big black holes, however, the event horizon is so far from the center that those tidal differences can be quite gentle at first. You might cross the horizon without immediate disintegration, only to face stronger stretching deeper in. Think of it like walking over a steep hill versus a long slope, same drop overall, but how sudden the fall feels depends on the hill's size. We observe the effects of the event horizon and the pull toward the singularity indirectly, by watching matter and light behave near black holes. Hot gas forms bright spirals around the outside, light bends into weird paths, and sometimes jets shoot away along the poles. Those telltale signs act like footprints on a beach. You can't see the creature itself, but you can deduce a lot from the prints. Meanwhile, the singularity remains the part of the picture that challenges our theories, a place where physicists swap equations like chefs debating a recipe and still suspect there's a missing ingredient. A little mystery remains, and that is both scientifically healthy and, depending on your tolerance for cosmic danger, mildly entertaining. How black holes warp spacetime. Massive objects bend the fabric of space and time, and black holes do this more extremely than anything else we know. Picture space and time as a stretchy sheet. Anything with weight makes a dent in it, and the heavier the object, the deeper the dent. Put a bowling ball on a trampoline and roll a marble nearby. The marble will curve around the bowling ball not because something is pulling it with an invisible rope, but because the trampoline is tilted. That simple picture is how gravity works in everyday terms. Closer into a black hole, the dent becomes so steep that paths through space and time twist inward, and things that get too close follow those bent paths right toward the center. Orbits are just objects following curved paths in that stretched sheet, which is why planets go around stars instead of flying off in straight lines. Even time gets stretched. Clocks deeper in a gravity well tick more slowly compared with clocks farther away, and this is not a sci-fi idea. GPS satellites have to account for it every day, or their positions would drift by kilometers. It's like time being a lazy river that slows down when it goes into a deep pool. Tidal effects show another side of how the warping works. Gravity near a black hole can be very different a few meters apart. Your feet might feel a stronger pull than your head if you got too close, and this difference stretches objects lengthwise and squeezes them sideways. Think of pulling a piece of taffy. The center thins and the ends stretch. Astronomers call the extreme version of this spaghettification, which sounds silly until you picture a safely cooked spaghetti noodle becoming a little too literal. Light, too, follows the warped paths. Instead of going straight, a beam of light will bend when it passes near a heavy object, so distant objects can appear shifted or even produce multiple images, like looking through a funhouse wine glass. The effect is used as a tool by astronomers to map mass that we can't see directly. And the closer you get to a black hole, the stronger all these effects become. Far away, the dent in the cosmic sheet is small and almost unnoticeable. So while a black hole warps spacetime in powerful, sometimes strange ways, the strength of that warping depends entirely on how deep the dent is and how close you are to it, which is a comforting thought unless you're the marble rolling down the trampoline toward the bowling ball. Tidal forces and spaghettification. On Earth, the moon's gravity pulls on different parts of the planet a little bit differently, and that small difference is exactly what makes tides rise and fall. Tidal forces come from variations in gravity across an object. The side closer to a mass feels a stronger pull than the far side. This is why oceans form bulges toward and away from the moon, and why a long object stretched into a strong gravity field will feel a pull that is stronger at one end than the other. It sounds simple, but that gradient, the change of pull over distance, is the key idea behind the dramatic stretching near a black hole. Close to a black hole, the same difference in pull becomes extreme. Instead of millimeters of ocean rise, the pull on your feet could be far stronger than on your head, because the black hole's gravity changes very rapidly with distance. Picture holding a piece of taffy by one end while someone else pulls the other. The farther their hand is from yours, the more the taffy elongates. That visual helps explain spaghettification. Objects are stretched into long, thin shapes along the line pointing to the black hole while being squeezed sideways. It's like cosmic taffy, but less tasty and more terminal. For ordinary everyday scales, like people and cars, the tidal differences on Earth are tiny and harmless. Examples from daily life make this clearer. You feel only one gravity pulling you down, not two different strengths, so you don't get stretched out when you stand up. By contrast, near a compact, dense object, the pull changes so fast that structural bonds, molecular bonds, then atomic bonds, are strained and eventually torn. Long things, such as trees or buildings, would be pulled apart first at the points where the gradient is steepest. Short things are safer only until the gradient becomes enormous, then nothing is safe. Not all black holes act the same. For very small, dense ones the tidal gradient at a close distance is enormous, so spaghettification begins well before you cross any invisible boundary. For extremely massive black holes the gradient at the boundary where you cross might be gentler, so you could pass a short way inside before stretching becomes catastrophic. This depends on how mass and distance trade off. The strength of the tide grows quickly as you get closer, roughly in proportion to mass divided by distance cubed, which means small changes in distance can make a huge difference. In practice that means the neighborhood around a black hole can be calm one moment and violently deforming the next. A few practical mental images help. Think of ocean tides, rubber bands, and pulling apart taffy. Picture a long rope with one end near the black hole and the other far away. The end closer to the hole is yanked much harder and the rope would thin and lengthen. A little humor is allowed here, call it the universe's pasta machine, but the physics is merciless. If something approaches close enough, structures break, molecules separate, and ultimately matter streams inward as a thin thread of material. The process is slow at first for large objects, then accelerates into an extreme stretch. There is no safety net once the tidal forces win. Defining dangerous distances, Roche limits and beyond. Tidal forces are the name of the game when a massive object passes nearby. A simple way to think about them is to picture a tug-of-war where one side is closer to the rope. The closer end feels a stronger pull than the far end. On a planet, that difference in pull across its diameter is what stretches and squeezes it, and if the difference becomes larger than the planet's own gravity holding it together, pieces start to come off. This critical distance depends on how tightly held together the planet is and how concentrated the passing object's mass is. In plain terms, if the pull varies enough from one side of Earth to the other, structural integrity fails, and that's when things get ripped apart. Everyday examples help. The moon raises tides on Earth because the pull on the near side is a bit stronger than on the far side. This is the same effect on a gentler scale. Saturn's rings give a clearer demonstration. A moon that strayed too close to Saturn would be torn apart by tidal forces, and the rubble now forms the rings. Scientists use these ideas to calculate a no-go zone around a massive object. The mathematical rule behind it says tidal strength grows very fast as you get closer. Specifically, the stretching effect scales roughly with the mass of the visitor divided by the distance cubed, so moving half the distance increases the tidal difference by about 8 times. That steep curve means there's a narrow threshold where things go from mildly uncomfortable to catastrophic. Black holes add an extra twist because of their compactness. Two things matter most: the black hole's mass and how close it comes. A small, stellar mass black hole has its intense gravity packed into a small region, so the zone where it would shred Earth might be dangerously close but still outside its point of no return, the event horizon. The event horizon is simply the boundary beyond which not even light can escape. Crossing it means no comeback. By contrast, for extremely massive black holes, the shredding zone can lie inside that horizon, which means an object would cross the horizon before being torn to pieces by tides. In casual terms, with some black holes you'd be swallowed whole before you felt the peel, with others, you'd be stretched like dough and then swallowed. Both are bad for a picnic. Danger doesn't only mean immediate breakup. At distances larger than the shredding point, tidal effects can still strip atmosphere, drive massive ocean bulges, trigger earthquakes, and upset orbits of satellites and the moon. A close flyby could nudge Earth into a different orbit, change rotation speed slightly, or destabilize the moon's orbit, and those changes would have cascading effects on climate and tides. Think of it like a passing truck creating a large wake. Leaves might not fly off the tree, but unsecured garden furniture will, shingles could come loose, and windows might rattle. Timing matters too. A fast, brief flyby gives less time for orbits to change much, but the instantaneous tides can be extreme. A slow passage allows cumulative effects to build up and can be worse in other ways. Putting this into practical language, there's an inner danger zone where tidal forces would literally break the planet apart, a middle zone where atmosphere and surface effects would be severe without total destruction, and an outer zone where long-term orbital changes become the main worry. Which zone you end up in depends on the black hole's mass and the close approach distance. Observationally, we'd see growing anomalous tides, shifts in satellite orbits, and gravitational anomalies well before anything dramatic happened. So while the "will Earth survive?" question sounds dramatic, survival and the degree of damage are determined by these distance-based thresholds, and by whether you like your coastline as it was yesterday. Passing versus capturing, encounter types. When a massive object swings past a planet, there are basically two ways the meeting can go: it either zips by and keeps going, or it loses enough energy and ends up trapped, circling the planet like an unwelcome houseguest. A passing encounter is like a car speeding past you on the highway. The path is bent a little by gravity but the visitor keeps going. A capture is more like a car being pulled into a roundabout and forced to circle. It no longer has the same freedom to leave. Which of those happens depends on speed, distance, and whether anything can take away energy from the incoming object. Speed matters more than people expect. If the intruder is moving fast relative to the planet, gravity can only bend its path. It's hard to stop something that already has a lot of forward motion. Slow approaches are the ones that can be trapped. Think of trying to catch a frisbee. If it's thrown hard, you might miss. If it drifts slowly toward you, you can grab it. In space terms, to go from a passing path to a bound orbit you have to remove just enough of the object's energy so that it can't escape again, and nature doesn't hand out breaks for free. Distance at closest approach is the next big factor. A distant flyby tugs gently and nudges the orbit a bit, similar to how a passing truck makes your house tremble a little. A close pass lets gravity do heavy lifting. The tug becomes strong enough to change the visitor's fate. For small bodies like pebbles or loose debris, passing very close to a planet with an atmosphere can mean the intruder will hit the air and slow down enough to be captured or to burn up. That's why spacecraft sometimes deliberately dip into thin upper atmospheres to lose speed and settle into orbit. It's called aerobraking and it's a deliberate, controlled form of let the air act as a brake. Mass and interactions with other bodies play a big role too. A planet is more likely to capture something if a third body can steal energy during the encounter, a kind of cosmic three-way where one object takes momentum from another and lets it fall into orbit. That's how small moons can be captured. They lose energy by interacting with other moons or passing through gas and dust long ago. In everyday terms it's a bit like one skater transferring momentum to another on an ice rink, so one of them slows down and the other speeds off. When the visitor is a black hole, the same principles apply but the stakes are higher. If a black hole flies past quickly and at a safe distance, its gravity will twist Earth's path a little but it will be a passing event. If it came in slowly and close enough, things get messy. Capturing a planet usually requires the planet or the black hole to lose orbital energy, and in many close, slow encounters the tidal forces are enormous, strong enough to stretch and heat a planet before it settles into a peaceful orbit. Think of that stretching like kneading bread, except the bread is a planet and the kitchen is on fire. Real-life analogies help. Gravity assists used by spacecraft are clean examples of passing encounters, where a planet gives a spacecraft a shove and the craft keeps heading outward. A captured example is like a satellite that slows in the atmosphere and ends up bound to Earth. Sometimes capture isn't gentle, braking, heating, and collision can accompany it. A very close interaction can break an object into pieces that then either fall in or form new rings or moons. So, whether a passing massive object becomes a wanderer or a new companion comes down to how fast it's moving, how close it gets, and whether there's a way to get rid of extra energy. Short answer: passers-by are common, true captures are rarer and usually require extra help or a violent close encounter. And no, the universe won't politely stop and ask for directions. It plays by energy budgets and distance, and those determine who leaves and who stays. Trajectories, speeds, and relativistic effects. Earth orbits the Sun at about 30 km per second, so any passing object has to be considered against that background motion. When a black hole flies through space near Earth, what matters most is the shapes of the paths involved, whether the paths cross gently, graze closely, or line up to grab a planet into a new orbit. Gravity changes straight-line motion into curved paths. Think of a marble rolling across a stretched rubber sheet that sags where a heavy ball sits. If the black hole's path comes far enough away, Earth's path will bend a little and carry on, like a car nudged by a passing truck. If the approach is closer, trajectories can change dramatically. Earth might be shifted into a new, elongated orbit, it could be flung outward, or in extreme geometry the planet could be captured into orbit around the intruder. The speed of the passer matters as much as the route. A fast flyby gives gravity less time to do its work, so a very quick encounter tends to only deflect trajectory slightly. Conversely, a slow, close passage allows the black hole's pull to act longer, increasing the chance of large orbital shifts or even capture. There is another useful idea here. Gravity's influence falls off with distance according to an inverse square rule, meaning doubling the distance cuts the pull to a quarter. Picture how a scent from a bakery becomes faint as you walk away. The closer you are, the stronger the effect. Spacecraft engineers take advantage of these path and speed interactions all the time with gravity assists, where a carefully planned pass past a planet changes a probe's speed and direction without burning fuel. Relativistic effects come into play only when speeds or gravitational strengths reach extreme levels. The speed of light is about 300 km per second, and most objects in the galaxy move at a very small fraction of that, so everyday encounters do not produce noticeable relativistic time shifts. Two kinds of relativity matter here: motion-related time dilation, where a moving clock ticks more slowly from the viewpoint of a distant observer, and gravity-related time dilation, where clocks deeper in a gravity well run slower compared to those farther away. GPS satellites already need both corrections to keep your phone pointing to the right coffee shop, which is a neat reminder that relativity is practical, not just science fiction. However, unless a black hole were moving at a large fraction of light speed relative to Earth, or Earth came extremely close to the black hole's event horizon, these effects would be tiny for daily life on the surface. Tidal effects are where speed and relativity combine with geometry to determine real physical consequences. Tides arise because gravity is stronger on the side of an object closer to the source than on the far side. In extreme cases near compact objects, this difference can literally stretch things apart, a process sometimes nicknamed spaghettification. For a distant, fast-moving black hole, the tidal gradient across Earth would be small and you'd feel only a subtle change in orbit. For a slow, close approach, the gradient could be steep, causing severe deformation or even disruption. A helpful household analogy is pulling a piece of taffy slowly versus snapping it quickly. The slower, steady pull can elongate and deform the candy much more noticeably than a short, sharp tug. Putting these pieces together, survivability is ruled by geometry and duration more than by dramatic-sounding labels. A passing black hole that keeps its distance and rushes by quickly would mostly leave Earth's orbit nudged or a bit perturbed. Think of a gentle pothole encounter on a long road trip. If it moves slowly and threads a close path, then gravitational forces and tidal gradients can do serious damage, and relativistic time effects would become a noticeable curiosity for outside observers. In short, whether Earth survives depends on the exact route and timing. Speed alone doesn't tell the whole story, but it does help decide if the meeting is a brief hello or an unwanted extended stay. Rogue and primordial black holes, cosmic drifters. Some black holes wander through space alone, not tied to a galaxy or star, and they can be very different from the ones sitting quietly at the centers of galaxies. One kind forms when a very heavy star ends its life, and the collapse or a violent kick from a companion star can send the newborn hole drifting away like a runaway shopping cart. Another kind is a theoretical idea: tiny, very old black holes that might have formed when the universe was extremely dense, long before stars existed. Scientists call the first kind rogue, because they roam, and they call the second kind primordial, because they would come from the universe's earliest moments, but you don't need to keep those labels in your head. Think of them as the vagabonds and the ancient seeds of the cosmos. Rogue black holes usually carry the heft of a star, so they behave like heavy, compact objects moving through space. They often go unnoticed until they interact with something. Gas falling in can light up like a campfire, or their gravity can bend light from a background star. Detecting them is a bit like spotting a car by its headlights at night. We don't see the car directly, just the light it produces or the way it changes things around it. Astronomers use clever tricks such as watching for a star to brighten and dim oddly when a massive object passes in front of it. This bending of light acts like a natural magnifying glass in space. Primordial black holes are a different, more speculative story. They could be very small compared to star-formed holes, perhaps even smaller than an atom, yet packed with a surprising amount of mass. That sounds like science fiction, but the key point is that if they exist they would have formed from tiny fluctuations in the very early universe and might be scattered throughout space. Finding one would be like discovering an old coin in a field, rare and valuable, but you have to know what to look for. Because they might be small, they wouldn't always produce bright light when they pull in gas, so we look for subtler signs, tiny lensing events or faint ripples in space itself. Detecting these drifters requires patience and a mix of techniques. Telescopes search for sudden brightening of stars, radio telescopes listen for energetic emissions, and instruments that measure the fabric of space can catch passing ripples if two heavy black holes collide. A helpful everyday analogy: if you wanted to know whether a bus passed on a quiet street at night without turning on headlights, you could look for the shadow it cast on a lamppost, listen for the rumble on the ground, or notice the leaves it stirred. Similarly, astronomers check for light bending, soundless ripples in space, and the faint glow from material being pulled in. In practical terms, these cosmic drifters are more curiosity than immediate danger. Space is vast and the odds of a close encounter are vanishingly small, so it's not worth moving to the hills. Still, understanding them matters because they teach us about how stars die, how galaxies evolve, and perhaps about conditions in the very early universe. A rogue black hole is like a stray dog. It can be noisy and dramatic if it gets too close, but most of the time it wanders the neighborhood without bothering anyone. A primordial black hole, if real, would be more like a tiny relic in your attic, quiet, mysterious, and unexpectedly informative. How common are close encounters? Most black holes are simply too far away to bother Earth, whether they started life as massive stars that collapsed or sit quietly in the middle of a galaxy. They exist, yes, and many are scattered through the Milky Way, but space is enormous and objects are spaced out. Think of the galaxy as a huge parking lot and black holes as a few cars parked far apart. The chance one will suddenly pull into your driveway is extremely small. Some black holes wander through the galaxy after getting a kick when they formed, so a lone one moving through space is possible. Astronomers don't just guess about this, they watch millions of background stars for tiny brightening events called gravitational microlensing, which happen if a compact object briefly passes in front of a more distant star. Telescopes catch these blips and help count and characterize roaming dark objects. It's like watching a busy highway from an overpass to see how many vehicles pass, rather than waiting at your mailbox for a delivery that will never come. Even if a black hole were headed this way, its gravity drops off fast with distance, so it would need to come very close to the inner solar system to tug on Earth or on the planets. For comparison, a strong magnet held across a room won't make your keys slide across the table. Likewise, a distant black hole won't fling comets or rearrange orbits, only a near miss, inside the outer reaches of the solar system, would create serious gravitational trouble. We'd be able to see signs long before anything dramatic happened: shifts in the paths of comets, small but measurable pulls on nearby stars, or the characteristic microlensing flashes. Astronomers combine those observations with models of where stars and remnants tend to be, and the picture that emerges is reassuring. There are likely many stellar mass black holes in the galaxy, but they are distributed over such vast volumes that a close encounter with Earth is, for all practical purposes, not on anyone's short list of concerns. So Earth surviving a random black hole photobomb is not something to lose sleep over. Your bedtime worries can stay focused on bills and the neighbor's overly friendly cat instead. The solar system's gravitational context. Most of the mass in the solar system sits in one place, the Sun, which makes up about 99.8% of everything there. That sheer weight means the sun's pull is the main reason planets, comets, and asteroids follow the paths they do. Think of the sun as a very heavy person sitting in the middle of a trampoline while the planets are kids running around the edge. The dip in the fabric keeps them rolling in circles instead of shooting off in straight lines. Planets stay in steady paths because two things balance out: gravity pulling them in, and their forward motion trying to fling them outward. On Earth we feel that balance as seasons and predictable skies. The planet is racing around the sun at roughly 30 kilometers every second, yet we don't fly off because the sun's gravity keeps tugging. A helpful everyday comparison is twirling a ball on a string. The string pulls the ball inward and your spin keeps it from crashing into your hand. Same idea, but on an enormous scale and without any actual string. Not every object in the system is equal. Jupiter is the heavyweight among the planets, with a mass over 300 times that of Earth, and it acts like the big sibling in a chaotic playground. It can fling passing comets and asteroids away, or steer them inward toward the inner planets. Trojans, little rocky companions, sit in stable spots ahead of and behind Jupiter in its orbit. They are like people sitting on the benches that never move while the game goes on around them. Those stable spots exist because the tug-of-war between Jupiter and the Sun creates quiet zones where smaller bodies can stay put. Every planet has a local region where its own gravity wins over the Sun's pull. This is the area where moons and satellites can comfortably orbit. For Earth, that neighborhood stretches roughly 1.5 million kilometers out, so the Moon sits well inside our gravitational zone. Close to home, the Moon's slightly stronger pull on the near side of Earth compared with the far side produces the tides, simple, visible proof that gravity isn't the same everywhere at once. It's the difference between someone giving your shoulder a squeeze and someone pinching your sleeve: similar action, different strength. Out past the planets, the Sun's grip gets weaker and the neighborhood becomes messy. Small, distant objects feel tiny nudges from passing stars, giant planets, and the combined gravity of the Milky Way itself. Picture driving a car down a long empty road. A gust from a passing truck can send a flurry of leaves spinning and changing course. In the outer reaches, those nudges can send comets inward or scatter them outward, because the Sun's hold there is no longer absolute. The solar system's gravitational map is therefore a mix of strong local wells and broader, more fragile areas where outside influences can leave a mark, often in ways that are surprising and sometimes a little dramatic. Perturbing planetary orbits, mechanisms of instability. A nearby massive object can change how planets move simply by tugging on them with gravity. Gravity gets weaker with distance following the inverse square rule. Double the distance and the pull becomes 1/4, but the difference in pull across a planet or across a planetary system can matter even more. Tidal forces are the key idea here. They are the difference in gravity felt at one side of an object versus the other. The Moon makes tides in Earth's oceans because one side of Earth feels the Moon's pull a little stronger than the other side. A passing black hole would create giant versions of that effect across an entire solar system, stretching some orbits and compressing others. A fast flyby mostly gives brief nudges. A slow, close passage gives larger, lasting changes. Short interactions can be compared to an unexpected shove on a crowded bus. Everyone wobbles but quickly settles. Slow, sustained tugs are like a steady push that can topple a standing row of books. The amount of change depends on the black hole's mass, its path through the system, and how close it comes to any given planet. Lighter, fast-moving ones tend to scatter small objects out of distant regions, while heavier or slower ones can rearrange the architecture of whole planetary systems. Resonances amplify small effects into big ones over time. When two objects line up in their orbits in a repeating pattern, small tugs can stack up. This is called mean motion resonance. Push at the right rhythm and the swing goes higher. In planetary systems, a passing mass can move bodies into new resonances, or knock them out of stable ones. The result can be more elliptical orbits, that is, more stretched paths, or shifts in orbital timing that cause long-term instability. Spacecraft engineers exploit similar exchanges of energy when they borrow speed from planets during gravity assist maneuvers. The same physics works in reverse when a rogue massive object steals or gives orbital energy. Inclined encounters can tilt or flip orbits through a mechanism that trades tilt for orbit stretch. Simple terms, an external tug can convert a planet's tilt relative to its star into a more elongated path, or vice versa. This oscillation between tilt and stretch is similar to how a wobbling toy can swap sideways motion for up and down motion. If a planet's orbit becomes much more elongated, its climate can swing wildly between slow, cold stretches and brief, scorching passes near the star. Small creatures might find that unpleasant. Long-term chaos can follow when multiple planets perturb each other after being nudged. Little differences grow and predictability disappears, much like two slightly different pushes to a double pendulum soon lead to wildly different swings. Distant reservoirs of small bodies are especially vulnerable and act like a warning system. Far-out clouds of comets and icy bodies sit loosely bound to stars, and a passing black hole can shake that cloud and send a volley of comets inward. Think of it as knocking over a grocery display. The spill reaches the checkout lane. Those inbound comets raise the chance of impacts and can indirectly alter planetary orbits through countless small collisions and gravitational encounters with planets. Scattering events can also directly eject a planet into interstellar space, or send it plunging inward to collide with its star or other planets. Billiard ball collisions are a useful image here. A close gravitational encounter between a planet and a massive passing object can transfer momentum in a single, decisive exchange. Not every encounter is catastrophic. Many flybys leave planetary systems only slightly perturbed, shifting orbital shapes or years by small amounts. But the difference between small and big changes often lies in timing, distance, and repetition. Repeated small nudges, properly timed, build up like rhythmic pushes on a child's swing. A single massive, slow flyby can be like a hand grabbing the swing and flinging it high. The practical takeaway is that the mechanisms of instability are familiar: tides, resonant builds, exchanges of energy and momentum, scattering and comet showers, all straightforward processes that, when combined, can rearrange or ruin planetary order. And they do it with a kind of elegant ruthlessness that would make a cosmic bully proud. Could Earth be ejected from the solar system? Earth orbits the Sun because gravity keeps it tied in a fairly steady path, and that motion has real numbers behind it. The planet moves around the Sun at about 30 kilometers per second, while the speed needed to break free from the Sun's pull at Earth's distance is about 42 kilometers per second. In plain terms, Earth would need a push that changes its speed by roughly 12 kilometers per second in the right direction to sail off into interstellar space. Those are big numbers. They're not something a passing comet could casually provide. One way an ejection could happen is through a close gravitational encounter. Picture two dancers on a crowded floor and a third, much bigger dancer barges through. One of the smaller dancers might get shoved out entirely. In space, this is the gravitational slingshot or three-body interaction. A heavy object passing near the Sun-Earth pair can steal or give energy to Earth's orbit and send it onto a new path. A simple backyard example is swinging a ball on a string and letting it hit a moving object. The ball can suddenly fly off faster or slower depending on how it meets that object. The same physics applies, just with celestial bodies instead of a ball and a post. For Earth to actually be flung out, the interloper would have to be both massive and come very close. Giant planets can do this during the early, messy phase of a planetary system. When gas giants scatter around, they can toss smaller worlds into wild orbits or out of the system entirely. Our own Jupiter is enormous compared to Earth, about 318 times Earth's mass, and in other solar systems similar giants have likely ejected planets. But our system is old and relatively settled now, so those violent rearrangements are unlikely. A passing star or a compact object like a black hole would need to slip well inside the outer reaches of the planetary system to strongly disturb Earth's orbit. Because black holes are very compact, they can get closer before hitting anything, but they still have to pass uncomfortably close, on the scale of the distances between planets, to deliver the kick Earth would need. This kind of deep, close encounter is extremely rare in the kind of quiet stellar neighborhood we live in. Astronomers do find free-floating planets and evidence that ejections happened elsewhere, so the mechanism is real. It's just not something that commonly happens to inner planets in mature systems. Think of it like a tornado in a wide-open prairie, possible, and dramatic when it occurs, but not something you expect during a calm afternoon picnic. On the bright side, if a black hole did slip by stealthily, it would be more likely to disturb the outer parts of the solar system first, the distant comet reservoir, before making the perilous trip close enough to rearrange Earth's orbit. If Earth were booted out, it would become a rogue world, no longer circling the sun. Life, if still around by then, would face a very cold future without the steady light and warmth of our star, though thick atmospheres or internal heat could buy time in niches. Think of microbial life under icy crusts rather than people sunbathing. So while gravitational physics shows ejection is possible in principle, in practice it takes a rare and dramatic encounter to make it happen. It's the sort of cosmic misstep you'd only expect to see in a science fiction thriller, or in a universe that enjoys surprising party tricks. The Earth-Moon system under stress. The Moon orbits about 384,400 kilometers away and has roughly 1/81st of Earth's mass, facts that matter because the two bodies are locked in a gravitational dance that shapes tides, day length, and even the tilt of Earth's axis. Right now the Moon slowly moves away at about 3.8 centimeters per year, a tiny change most of us never notice. A passing black hole would act like an unexpected, very strong partner barging into that dance. Its gravity wouldn't pull everything equally, and the difference in pull across the Earth-Moon pair is what causes the trouble. Think of the situation like two people holding hands on a small boat, and a sudden tug on one of them from the dock. The person on the dock represents the black hole. If the tug is light, the pair adjusts and keeps holding hands. If strong, one person might be jerked away or the rope could snap. The tug here is a gradient in gravity. The side closer to the intruder feels a stronger pull than the far side, and that gradient can stretch or squeeze both Earth and Moon. For the Moon, this could change its path from a neat circle to a stretched ellipse, or even kick it onto a course that slowly drifts away or crosses Earth's path. If the Moon's orbit becomes more elliptical, tides would become more extreme. High tides could reach farther inland and low tides could expose larger areas of seabed. Coastal cities and wildlife would face new challenges. Think of harbors where ships suddenly sit on mud flats at low tide, or storm surges mixing with rain-shifted tidal cycles. Ocean currents, which depend on the regular timing and height of tides as well as the steady tilt of the planet, would likely shift too, altering climate patterns and the distribution of nutrients that sustain fisheries. The Moon also acts like a stabilizer for Earth's tilt. Lose or substantially rearrange that stabilizer and the axis of Earth could wobble more wildly, making seasons swing in severity over long periods. That wouldn't mean instant apocalypse, but ecosystems and agriculture tuned to predictable seasonal rhythms could struggle to adapt. Moreover, when orbital energy is redistributed by a close encounter, Earth's rotation can speed up or slow down, changing the length of a day. You might get mornings that last noticeably longer or shorter. Alarm clocks would complain. In the most extreme close encounters, tidal forces from the interloper could overpower the gravity holding the Moon together, pulling it apart into debris that might form rings or rain down as meteor storms. Picture smashing a coconut and finding the meat scattered everywhere. Those fragments could pepper Earth, causing regional destruction where they strike and filling the sky with streaks of fire, beautiful to look at, dangerous to live under. All of these outcomes depend on how massive the passing object is and how close it comes. A distant pass would be little more than an unsettling bump. A close one would rearrange the familiar relationship between Earth and its companion. Immediate geological responses on Earth. A passing compact object would squeeze and stretch Earth unevenly, and the planet's outer shell would respond almost immediately. The key idea is simple: gravity would pull harder on the side of Earth that is closer and less on the far side, creating a tug-of-war across the planet. That tug is what scientists call a tidal force, but you can picture it as someone grabbing one end of a blanket while someone else holds the other. The blanket stretches and the wrinkles shift. Rocks that normally sit calmly under steady stress would suddenly feel extra pulling or pushing, and brittle parts of the crust would break. Faults already teetering on the edge of slipping would be the first to go, producing strong earthquakes right away. Seismic waves would race through the ground like ripples from a stone thrown into a pond. Earthquakes would not be confined to a single spot. Shaking could pop up in many places that were already weak. The ground could vibrate for a long time afterward, with main shocks followed by many smaller quakes. Think of a big tree branch breaking and then a shower of twigs falling. Soft, water-saturated soils would behave oddly too. They can temporarily turn into a soupy, unstable mess, causing buildings to tilt or sink. That is called liquefaction, and it's roughly like walking on a very bad pudding. Volcanic systems would also react. Magma sits under pressure in underground chambers, and a sudden change in the squeeze on the crust can open or close pathways for that molten rock. If pressure is reduced locally, gases trapped in magma can expand rapidly, a bit like shaking and then opening a soda can, and that expansion can help trigger an eruption if the volcano was already primed. Rocks shifting can also shear open new cracks that let magma rise more easily. So regions with restless volcanism could see sudden increases in activity, while calm volcanoes less ready to erupt might stay quiet. The oceans would not be spared from the immediate effects. Rapid changes in gravity and abrupt vertical movement of the seafloor would displace enormous volumes of water, launching waves that travel great distances. These waves are tsunamis in the technical sense, and they form when the seafloor moves up or down quickly, like slapping the bottom of a tub and watching the water surge. Coastal regions would face extreme currents and flooding from such events, and harbors could see ships torn from moorings or slammed into shore. Strong, persistent tidal bulges would make high and low water levels wildly different from the usual rhythms. On a global scale, the whole planet could be nudged into new patterns of motion. Earth might wobble differently on its spin axis or change its rotation rate slightly, which would alter the length of a day by some amount. The solid planet could also be excited into global standing vibrations. Physicists call these normal modes, so Earth would literally ring like a struck bell for a while. Those changes could also perturb flows in the liquid outer core, and because those flows generate the magnetic field, transient changes in magnetism are plausible. These effects are complex and coupled, but the immediate geological picture is one of sudden mechanical stress, rapid shaking, and rearrangement of underground fluids and molten rock. Infrastructure would take a beating where the shaking and ground failure occur. Roads could buckle, bridges could collapse and pipelines could rupture. Short. Engineers plan for earthquakes, but this would be a different sort of stress pattern and in places not normally prepared, so damage could be widespread. In short, the ground would not behave politely, it would creak, snap, slosh and sometimes explode, and the consequences would be felt from deep underground all the way to the coast. Oceanic responses, megatides and tsunami risks. Tidal forces happen because one side of our planet feels a slightly different pull than the other when another massive object is nearby. The moon makes the familiar ocean bulges that give us high and low tides, because it pulls on the near side of Earth more strongly than on the far side. Think of it like a tug-of-war where one team is a little closer to the rope bends toward them. In everyday life you see a similar effect when you rock a bathtub and the water sloshes toward the end you pushed. A passing black hole would change that tug dramatically if it came close enough. The strength of the pull doesn't just get a bit stronger as something approaches, it can increase extremely fast with decreasing distance, so a small change in how near it is can mean a huge change in the water's response. That can produce megatides, enormous rises and falls of ocean level, much larger than anything the moon or sun normally cause. These bulges could stretch over thousands of kilometers and create crushing currents between high and low areas. Harbors could fill and empty quickly, piers could be torn off their foundations, and ships might be slammed ashore or flipped in narrow channels. Not a good day for beach volleyball. Tsunamis are different from slow tidal bulges because they are fast-moving, sharp waves caused by sudden shifts in the water's base, typically from the seafloor moving, landslides, or large impacts. A passing black hole could create tsunamis in a couple of ways, by pulling so hard that the seabed shifts or underwater slopes collapse, or by giving a rapid, uneven tug on the ocean surface that launches waves. Picture dropping a fist into a pond for a big ripple versus slicing the water quickly to send a fast wave. The latter is more like a tsunami. Once formed, these waves race across ocean basins and can amplify as they hit shallow continental shelves or get funneled into bays and harbors, doing much more damage than the same height of water on the open sea. There are further knock-on effects beyond the initial waves. Strong, changing tides set up violent currents that scour coastlines and trap boats. Sudden changes in salinity and temperature from massive mixing can harm fish and coral, and debris-laden water can bury coastal ecosystems. Critical coastal infrastructure, roads, bridges, ports, and facilities that rely on seawater for cooling, would face immediate threats. Early warning systems, tide gauges, and ocean buoys help today with earthquake-driven tsunamis, but if a gravitational encounter is extremely rapid, some coastal areas might get little notice. In short, the ocean's response combines slow, giant bulges and fast, destructive waves, and together they make for a very bad beach day, and a logistical nightmare for rescue teams. Atmospheric effects and mass loss scenarios. A nearby black hole would first make itself known by pulling unevenly on different parts of the air around Earth. Gravity from a very heavy object doesn't grab everything the same way. The side of our atmosphere closer to the intruder feels a stronger pull than the far side, and that difference stretches and shears the air. Think of stretching taffy or the way water sloshes farther on one side of a bathtub when you push the other side, except now that the slosh can be enormous and happen in the sky. Those uneven pulls set up huge winds and pressure differences, which can churn the atmosphere into violent flows that cascade down to the surface. As air is tugged and accelerates, some of it can be thrown away from Earth entirely if the pull is strong enough. When gas moves toward a compact, heavy object, it can heat up a lot as it falls, converting the pull of gravity into light and fast particles. That light and those particles can smash into air molecules and knock electrons off them. In plain words, the upper atmosphere gets ionized, meaning normal air gets turned into charged gas. This is similar to how a microwave heats water molecules, but with much higher energy light and particles. It can break apart protective molecules like ozone, letting more harmful ultraviolet light reach the ground. Also, when charged particles rain down along Earth's magnetic field lines, they create brilliant auroras, like the northern lights, but a passing black hole could make those displays furious and widespread, painting the sky everywhere rather than only near the poles. Earth's magnetic shield helps a lot, but it can be squashed. If the incoming object compresses the magnetic field, the shield becomes less effective at fending off charged particles, and more energetic stuff reaches lower layers of the atmosphere. Picture an umbrella being turned inside out in a gale. The protection is still there in shape, but it no longer keeps things out as well as before. At the same time, the motion of a black hole through the solar environment could set up a blast of particles and a wake, like a speedboat cutting through water. That wake acts like a strong wind pushing against the outer atmosphere. Scientists call this ram pressure, stripping away upper layers in a way not unlike how a strong wind can strip leaves from trees or how a vacuum cleaner sucks crumbs off a carpet. There are different ways the atmosphere can actually be lost. One is mechanical stripping, where pieces of the outer air are literally torn away and carried off into space. Imagine a punctured tire that hisses and slowly goes flat. The outer layers leak away. Another is energetic erosion, where high-energy photons and particles break molecules apart and heat the remaining gas until individual atoms gain enough speed to escape into space. Then there's direct feeding of the black hole. Some of the air could fall in and be added to the black hole's meal, literally becoming part of it. Which of these dominates depends on how close, how massive, and how fast the black hole is moving past Earth. A small, fast flyby might just ruffle the upper atmosphere. A slow, very massive passerby could peel chunks off like a giant cosmic apple corer. Short-term effects could range from spectacular auroras and temporary communication blackouts to serious increases in surface UV and atmospheric chemistry changes that harm crops and human health. Over longer periods, losing a lot of upper air changes pressure and temperature, shifting climate zones and possibly making the planet drier and colder or thinner and less able to hold heat. Recovery, if it were possible, would be slow. Replenishing lost atmosphere happens through volcanic outgassing and other geological processes that take ages. In extreme cases, the analogy is a balloon with a huge tear. You can try to patch it, but if the rip is too large, the air doesn't stay in, and the balloon won't hold shape again. So the human experience would be a mix of immediate turbulence and radiation headaches, followed by more subtle, longer-term changes in weather and habitability, depending on the severity of the encounter. Shelter can help. Underground or well-shielded structures reduce exposure to both particles and radiation, yet if the atmosphere itself thins dramatically, surviving outside those safe zones becomes a different problem. Whether Earth keeps most of its air or loses it in significant amounts comes down to the closeness and mass of the visitor and how much of the atmosphere ends up getting accelerated, ionized, or swallowed. From a practical standpoint, that means outcomes span from annoying and dangerous to truly catastrophic, which is a lot like getting splashed by a puddle versus being run over by a truck. Same water, very different results. Radiation hazards from accretion and jets. When a black hole rips gas and dust toward it, that material slams together and heats up until it glows in very energetic light like 10th rays and gamma rays. This glowing swath of hot matter acts like an enormous furnace, and sometimes the furnace shoots out narrow, powerful streams called jets that carry both light and high-speed particles. Think of the hot gas as a boiling kettle and the jets as a garden hose pointed in one direction. One makes steam, the other makes a focused spray that can go a long way if it's aimed at you. 10th rays and gamma rays are forms of light with so much energy they can knock electrons off atoms, a process called ionization. High-energy particles, protons, electrons, and heavier bits, are thrown out at near light speed and are often called cosmic rays. These forms of radiation can break molecules, damage living cells, and interfere with electronics. A relatable example: medical 10th rays can see bones, but too many of them are harmful, and airline crews get slightly more cosmic ray exposure than people on the ground because they fly higher. That gives a real-world taste of how layers above us normally reduce exposure. Earth's air and magnetic field do a lot of protection work. The atmosphere soaks up most 10th rays and gamma rays before they reach the surface, and the magnetic field bends many charged particles away. Still, very intense outbursts can create cascades of secondary particles in the atmosphere, like a billiard ball hitting a rack and sending many balls scattering, which can reach lower altitudes and change atmospheric chemistry. One consequence is that energetic particles can create nitrogen compounds that eat away at ozone, and that would let more ultraviolet light through from the sun, increasing sunburns and harming plants. Commercial aircraft and satellites are more exposed during these events, which can raise radiation doses for passengers and mess with satellites and GPS signals. Jets are narrow and directional, so whether Earth would be affected depends a lot on geometry. Most of the time a passing black hole wouldn't point a jet straight at us. Distance is crucial too. Radiation intensity drops as you get farther away. Even so, if a jet did hit Earth, we'd see effects similar to a very powerful solar storm but potentially much stronger. Satellite electronics can glitch or fail, power grids can be stressed by geomagnetically induced currents, and astronauts outside the protective blanket of low Earth orbit would be at high risk. Simple precautions help: hardening spacecraft electronics, planning radiation shelters for crewed missions, and keeping eyes on space with 10th ray and gamma ray telescopes for early warning. Yes, a pretty inconvenient cosmic neighbor, but not one you can handle with a better sunscreen alone. Magnetospheric interactions and biospheric shielding. Earth's magnetic field comes from the motion of molten metal deep inside the planet, and that field creates a magnetic bubble around Earth that deflects streams of charged particles coming from space. This magnetic bubble, often called the magnetosphere, steers most of the dangerous energetic particles away from the surface, channeling some down toward the poles where they make auroras. When that protective bubble is disturbed, the result is not just pretty lights. It can mean more high-energy particles reaching the upper atmosphere, more electrical currents induced in long conductors, and subtle changes to chemistry in the air that affects ultraviolet shielding. A massive object passing nearby would tug on the charged particles and the magnetic field lines, squeezing the magnetic bubble on the side facing the object and stretching it out behind like taffy. That's similar to what happens during a strong solar storm when the solar wind pushes the magnetosphere inward. The compressed region lets more charged particles get closer to the atmosphere, increasing ionization, basically knocking electrons free from atoms in the upper air. Increased ionization can change how ozone behaves, which in turn affects how much ultraviolet light reaches the surface. Some insect and plant tissues are sensitive to rises in UV, and humans get sunburned faster if shielding drops. Short sentence. Longer sentence. If the passing object is actively pulling in gas and dust and making jets, there could also be a local increase in high-energy radiation and fast particles aimed in many directions, but a quiet, non-accreting object won't be an obvious particle factory. Either way, changes in particle flux near Earth can damage satellites and electrical grids because induced currents flow in long metallic systems. Power lines and pipelines are especially vulnerable. Airline crews and passengers already receive a slightly higher dose of cosmic radiation at cruising altitudes. If the magnetosphere weakens even a bit, that dose rises, like turning up the background radio static. A short line for emphasis. Living creatures rely on magnetic and atmospheric shielding in surprising ways. Many migratory animals, from birds to sea turtles, use the subtle cues of Earth's magnetic field to find their way across thousands of miles, and abrupt shifts or noisy fields could scramble those signals so well that navigation behaves like a phone with bad GPS. Microbes and plants that live at or near the surface would not suddenly evaporate, but increased ultraviolet and energetic particles can stress photosynthesis and make some delicate species decline, which cascades through food chains. And yes, humans would notice household electronics acting grumpy and more satellites blinking out of service. That's the boring but real part of space weather. On the positive side, the atmosphere remains the heavyweight champion of shielding for most kinds of radiation. It absorbs 10th rays and soft gamma rays long before they reach people on the ground. Energetic particles that do punch through often create secondary particle showers higher up, and those showers are what aircraft crews and high-altitude passengers feel most. Still, if the magnetic bubble is squeezed hard and ozone chemistry is altered, the combination of increased particle flux and reduced chemical shielding could let more ultraviolet and energetic radiation through, enough to affect ecosystems and infrastructure, though not necessarily to make Earth instantly uninhabitable. A bit of surreal science fiction horror, wrapped in everyday consequences. Practical signs of magnetospheric disturbance would be obvious: unusually vivid auroras at latitudes where they don't normally appear, more satellite malfunctions, and regional power grid problems from induced currents. Simple precautions like hardening satellites, improving grid protections, and monitoring animal migration can mitigate many effects. In short, the magnetosphere and atmosphere together act like a layered umbrella. Poke a hole at the top and you don't get soaked immediately, but things underneath start to feel the drizzle, and some species and systems are less umbrella-ready than others. Accretion disks, bright signals and heat. Matter falling toward a black hole usually doesn't drop in smoothly. Instead it spirals into a flat, fast-moving disk, like water going down a drain but far hotter and much less friendly. As material whips around, it rubs against neighboring gas and dust, and that rubbing turns motion into heat, the same basic trick your car brakes use to stop, or your hands use to get warm when you rub them together. This heat makes the disk glow across many kinds of light, from visible and ultraviolet up to powerful 10th rays, depending on how close and how fast the gas is moving. The inner parts of these disks can get extremely hot. Around smaller, star-sized black holes, the innermost gas heats to temperatures so high that it emits 10th rays, which telescopes in space are built to catch. For the monster black holes at the centers of galaxies, the disk is usually cooler nearer the center in temperature terms, so more of the light comes out as ultraviolet and visible light. Those disks can be so bright they outshine all the stars in their host galaxy. Astronomers call such objects quasars. You can think of different disks like kitchen appliances, a small, furious stovetop burner, 10th ray, bright stellar disks, versus a huge oven glowing in visible light, supermassive disks. Astronomers read the fingerprints of disks by watching the light change. 10th-ray telescopes see rapid flickering when the inner disk shifts, erratic flashes much like a pot on a shaky stove that suddenly whistles. Long-term changes happen too, as more or less material feeds the disk and the whole glow brightens or dims. Instruments that look at radio waves often pick up narrow, powerful beams launched out from the poles of the disk, and those beams are another signal that a lot of energy is being processed near the black hole. The heat and light from an accretion disk aren't just pretty to look at, they push on and change the surrounding environment. Intense radiation can strip electrons off atoms, turning nearby gas into a charged, hot wind that gets blown away from the disk, rather like how a hairdryer evaporates moisture from a wet shirt. If a disk formed close to a planet, that high-energy light could heat upper atmospheres and erode them over time. On human scales it's a reminder that proximity matters. Still, no bright, sizzling disk appears unless there's a good supply of material to feed it, so a passing black hole would only cook up a dramatic light show if it managed to scoop up gas, dust, or a star to feed that spinning furnace. Hawking radiation and tiny black holes explained. Black holes are predicted to shine very faintly because of strange quantum effects happening right at their edges. Tiny disturbances of empty space briefly create pairs of particles and antiparticles, like brief sparkles in a dark room. Usually they recombine and vanish, but near a black hole one member of the pair can fall in while the other escapes, and that escaping partner looks to the outside world like radiation. This process effectively steals a bit of energy from the black hole, so over time the hole loses mass and slowly evaporates. Simple enough in words, but the physics behind those fleeting particle pairs comes from the rules that govern the very small, quantum mechanics, and how those rules behave in the extreme gravity near a horizon. Think of the event horizon as the rim of a fountain where water sometimes splashes out. One splash might be pulled back into the flow, while another clear drop flies off into the air and catches the sunlight. The drop that escapes is analogous to the particle that becomes real radiation, and the missing water is the black hole's lost mass. Smaller black holes behave very differently from the giant ones at the centers of galaxies. The less mass a black hole has, the hotter it is in this quantum sense, and the faster it radiates away. So a tiny black hole would be much more intense as a radiator than a giant one, and it would shrink faster because it is losing proportionally more of itself with each escaping particle. Observationally, the glow is effectively invisible for astronomical black holes because the signal is incredibly weak compared to the surrounding cosmic noise. Scientists have not seen this radiation coming from real black holes yet, so the idea remains a solid theoretical prediction waiting for direct confirmation. Researchers have created analog setups in laboratories, using flowing fluids, ultra-cold atoms, and light in optical fibers, that reproduce similar patterns to what the theory predicts, and those experiments give confidence that the basic concept is on the right track. Particle accelerators have searched for signs of tiny black hole production and found no convincing evidence, so if microscopic black holes exist they are either extremely rare or require conditions we don't reach in current machines. As a tiny black hole loses mass its temperature goes up, which makes it radiate more strongly, speeding up the shrinking in a feedback loop. The final phase of that shrinking would be rapid and energetic in theory, often described as a brief burst of high-energy particles rather than a slow fade-out. That sounds dramatic, but let's be practical. There is no observed case of such an event, and if micro-black holes could pop into existence on Earth they would evaporate almost immediately and leave little trace, not the stuff of apocalyptic cinema. In everyday terms, it's like a tiny sparkler that sizzles violently for a moment and then is gone, as opposed to a bonfire that keeps smoldering for hours. Explaining this to a non-specialist, the key points are clear and comforting. The process is rooted in well-established quantum ideas. Smaller black holes radiate more intensely than larger ones, and real astronomical black holes are expected to emit radiation so weak it's drowned out by their surroundings. Analog experiments back the concept. Searches in colliders have not turned up micro-black holes, and the dramatic final burst remains theoretical. So in the cosmic theater, Hawking-style radiation is a quiet but profound performer, subtle in most acts, potentially flashy only when the actor is extremely small. Gravitational waves from a near flyby. Gravitational waves are ripples in the fabric of space that show up when very heavy objects move in uneven ways. Scientists have actually measured these ripples from extreme events like black holes smashing together, proving the idea is real. Think of it like dropping a stone in a pond. The water makes rings that travel outward. The pond is space, the stone is the moving mass, and the rings are the waves. A black hole passing by would make its own set of ripples as it speeds and curves through space, but the strength of those ripples depends on how massive the hole is and how violently it moves. For most flybys, the waves would be incredibly faint by the time they reached Earth. The direct pull of the black hole, its gravity tugging at oceans and the ground, would be the thing to watch, not the soft whisper of the gravitational waves. Picture a big truck driving past your house. The rumble through the ground is the gravity tug, the tiny hum you might just barely hear through a window is the gravitational wave. These waves don't shove matter around like wind. Instead, they gently stretch and squeeze space itself in a back-and-forth pattern, and that stretching is tiny, so tiny that specialized instruments detect changes much smaller than atoms. Because the effect is so faint, gravitational waves from a single, distant flyby are more of a subtle note than a loud alarm. If you've ever felt a far-off bass line through the floor when a truck goes by, that's a useful, if imperfect, comparison. The truck's bass is the direct mechanical vibration, while the gravitational wave is more like a barely audible background tone. How much those ripples matter in a close encounter comes down to scale. If a black hole passed so near and fast that it produced very strong waves, everything else would already be in deep trouble from tidal forces and the overall gravitational pull. In that case, the waves are scientifically fascinating, but not the primary hazard. On the other hand, if the flyby is distant enough that the planet stays intact, the gravitational waves would be a faint scientific signal, interesting to detectors, rather than anything people on the ground would notice. Think of it as music at a party. A blaring speaker breaks the windows first, while the melody itself is only relevant to people listening closely. Detecting such a passing black hole via its gravitational ripples is possible in principle when the event is energetic and nearby, because the pattern of waves carries clear information about the motion and mass involved. The pitch of the ripple depends on how fast and how close the object moves, similar to how a siren changes tone as an ambulance speeds by. But for everyday safety concerns, these ripples are mostly a tool for scientists to learn about extreme behavior in space, not a direct cause of destruction. So while gravitational waves from a near flyby are a neat cosmic messenger, the real paperwork for survival would be about gravity's obvious pull, not the subtle shaking of space. Capture or collision, worst-case outcomes. A passing black hole that ends up pulling Earth into a new relationship would need to change the planet's motion enough that it slows down or is tugged into orbit. In simple terms, something has to act like a cosmic brake. That brake could be a very close, slow pass where gravity drains orbital energy, or it could be interaction with a dense cloud of gas that saps speed, scenarios that are rare but possible in principle. Think of a marble rolling across a table. If it hits a patch of sticky syrup, it slows and might start circling the sticky spot instead of continuing straight. The same basic idea applies to celestial bodies, only vastly more dramatic and with worse cleanup. If Earth were captured into orbit around the black hole instead of the Sun, the effects on climate and tides would be profound and fast-changing. Tides would not just be a higher high and lower low, they could become extreme, since the side of Earth closest to the black hole would feel a much stronger pull than the opposite side, stretching the planet and the oceans. That stretching can rip apart coastlines and set off giant waves. Small things on a beach day's scale become astronomical problems. Imagine every high tide powered by a bulldozer. The moon would likely not remain uninvolved. A new massive neighbor changes orbital dances, and the moon could be nudged into a different path, captured by the black hole, or thrown away entirely. Losing the moon or having its orbit altered would change night light, tides, and even the stability of Earth's tilt over long periods, which affects seasons. In everyday terms, it's like having the house thermostat suddenly controlled by a neighbor with a very different idea of comfort. Everything shifts and the house creaks. A direct collision or extremely close pass is even worse. If a black hole moved through or hit Earth, the intense gravity near its center would pull matter toward it, creating extreme heating and likely shredding planetary material. A small black hole might punch through like a bullet, leaving a catastrophic tunnel, strong seismic shocks, and lots of material thrown into strange orbits, while a sufficiently massive one could swallow the planet whole. Picture dropping a bowling ball through a soft fruit. Parts might be pushed aside, the fruit is destroyed. Now make the bowling ball invisible and millions of times heavier, and you get the idea. There would also be energetic flashes and particles as matter falls toward the black hole, which would be bad news for any nearby life. Debris and loss of atmosphere are additional, deadly consequences. Material pulled off Earth could form a hot disk around the black hole that glows and blasts radiation, frying surfaces and sterilizing neighborhoods on a planetary scale. If enough air is stripped away or the planet's spin and orbit are violently altered, the climate could swing to extremes or the planet could be flung into deep space with no steady sunlight at all. In short, capture or collision turns the usual safe, slow motions of planets into a chaotic demolition derby, and while it makes for dramatic science fiction, in reality it would leave Earth either radically altered or gone. Transit of a micro-black hole through Earth. A very small black hole passing through Earth would mostly tug on nearby bits of rock and air rather than swallowing the whole planet. Its gravity gets strong only when you are extremely close to it, so the region of strong influence would be cramped. Think a tiny, intensely hungry marble that only reaches out a millimeter or less. The part of Earth far from that close neighborhood would hardly notice the presence at all. Matter directly in the path could be pulled in and crushed, but the total amount is tiny because the black hole's cross-section is minuscule. Picture pushing a thumbtack through a ripe tomato. The skin and juice right at the tack's track get disturbed, but the rest of the tomato stays intact. In the same way, a micro-black hole would carve an almost invisible, very narrow trail through rock and molten interior, swallowing a little matter as it goes and possibly heating the immediately surrounding material. That heating and the sudden loss of tiny amounts of mass would send out waves. Seismometers would pick up a distinct, straight-line signal passing through the planet, unlike the curved waves from earthquakes. Short shocks could be felt locally along the path, and gases in boreholes might vent where the tunnel reaches the surface. Still, these effects would be more like a strange, sharp tremor than an apocalypse. Think of a single, strange ringing note rather than the whole symphony crashing down. There is also a theoretical twist. Very small black holes are predicted to give off energy and shrink in a process physicists call Hawking radiation. If that prediction holds, an especially tiny black hole might evaporate before it does much damage, releasing its energy in a burst. That would be dramatic to detectors but not likely to shred the planet. It's again comparable to a firework blink rather than a planet-sized oven. Probability matters too. The chance of a micro-black hole crossing Earth is vanishingly small, so it's not something to put in your emergency kit. If one did happen to pass through, scientists would study the event intensely, using seismic data, gravitational measurements, and any unusual radiation to learn about the object. In everyday terms, the world would be noisy for a short time, curious instruments would light up, and people would tell dramatic stories at dinner parties, but most cities would still be standing afterward. Long-term climate consequences after an encounter. A passing black hole would act like a very strong, sudden tug on the solar system, and that tug could nudge Earth's orbit and tilt in ways that change how sunlight hits the planet. Even small shifts in the amount of sunlight reaching different parts of Earth can change climate patterns. Think of it like moving a lamp closer to one side of a houseplant. One side bakes, the other wilts. If the tilt of the axis changes, seasons could become more extreme or milder in different places, altering when crops can be planted and when animals migrate. Farmers would notice first, because planting calendars are tuned to today's pattern of warm and cold, wet and dry. Another long-term effect comes from debris and comets. A strong gravitational disturbance farther out in the solar system could send a rain of comets and asteroids inward. When big pieces hit, they throw dust and soot into the atmosphere. That kind of sky darkening behaves a bit like giant volcanic eruptions do today. It can cool the surface by blocking sunlight, hurt plants by reducing photosynthesis, and trigger crop failures. The resulting climate stress could last long after the initial impacts because sunlight-blocking particles and chemical changes in the atmosphere can hang around or change ocean chemistry. Think of it like someone throwing a blanket over Earth. Temperatures drop and life has to cope. Massive heating can happen too, from internal effects. If the encounter stretches Earth even a little, tidal forces are the word for that stretching, it can produce extra heat inside the planet and stir up volcanic activity. More volcanoes mean more ash and greenhouse gases, which can both cool and warm the planet depending on which influence dominates. Acid rain from volcanic gases would stress forests and freshwater life. Coral reefs, already sensitive to small temperature and chemistry shifts, could suffer mass die-offs. That's not only bad for marine beauty but for fisheries people depend on. Wildlife would move, sometimes toward cooler or more stable areas, and some species would fade away if they can't adapt quickly. Oceans store most of Earth's heat and carbon, so long-term changes to ocean currents would be huge. If freshwater from melting ice or changes in wind patterns disrupt major currents, regions that used to be mild could become colder, while others heat up. Coastal fisheries would shift, and storms might rewire which areas get heavy rain versus drought. A shutdown or rearrangement of key currents is a bit like rerouting the heating system in a large building. Some rooms freeze, others sweat. Humans would see supply chain issues as fisheries collapse or move, and coastal communities might have to rebuild in different places. The atmosphere itself could be stripped away if the encounter is extremely close, but that is only a danger in the most extreme scenarios. More commonly, chemical balance would change. Greenhouse gases could rise from thawing soils and released methane or fall if aerosols dominate. Permafrost thaw is a useful example for today. When frozen ground melts, trapped carbon and methane escape and amplify warming. After a black hole-induced disturbance, similar feedback loops could either prolong warming or deepen cooling, depending on which processes dominate and how ecosystems and soils respond. Recovery would not be quick. Climate systems are slow to rebalance because oceans and ice hold memory of past conditions. Ecosystems recover in stages. Simple plants and microbes come back first, then insects, then larger animals over long stretches of time. Agricultural systems would need new crops and methods. Irrigation practices and seed varieties tuned to old climates might fail. Societies would adapt by moving production, changing diets, and investing heavily in climate engineering and large-scale restoration. Some changes would be permanent in human timescales, coastlines redrawn, species lost, and new climate norms set. It's like a house that suffered a flood. You can clean and rebuild, but the stain on the wall might never completely disappear. Practical human risks include supply shortages, increased migration, and infrastructure stress. Roads and power lines are not built for rapid freeze-thaw cycles or new flood plains. Cities might have to redesign water systems if rainfall patterns shift dramatically. On the bright side, people are adaptable. Seed saved in vaults, mobile greenhouses, and advances in desalination and renewable energy could cushion the blow. A little humor helps. Future gardeners might swap roses for hardy grasses and learn that climate-resilient crops make better neighbors than complaining tomatoes. Scientists would rely on models and observations to sort out these outcomes, watching changes in orbit, tilt, atmospheric composition, ocean temperatures, and ice volume. Monitoring would be crucial because small changes can cascade into big ones. In the meantime, examples from volcanoes, permafrost thaw, and coral bleaching today offer clues about what long-term stresses feel like on the ground, and they remind us that ecosystems and human systems can be pushed far from the comfortable conditions we're used to. Extinction risk and ecosystem resilience. A passing black hole close enough to tug noticeably on Earth would do more than make headlines. It could change the basic rhythms that life depends on. The strongest immediate effects would be the tugging forces that pull unequally on different parts of the planet, the same kind of pull that makes tides, but much stronger, which could trigger massive ocean surges and earthquakes. If the planet's orbit or tilt were nudged even a little, seasons could shift and rainfall patterns could move to places that are used to a different schedule, upsetting breeding seasons, plant flowering times, and migration cues for animals. In plain terms, when the timing of food and shelter shifts fast, many species struggle to keep up. Not all passes would do this. A distant flyby might be barely noticeable, while a close one would be catastrophic. It's like the difference between a noisy neighbor and a house being uprooted. Certain kinds of species would be much more at risk than others. Creatures that depend on very specific habitats, foods, or breeding sites, think pandas with their bamboo-only diet, or island birds that evolved without predators, have a narrow set of survival tricks. Fast, chaotic change tends to favor generalists, omnivores, scavengers, and opportunists such as rats or cockroaches that can switch diets and shelter quickly. Food webs are another weak spot. If a key pollinator or small fish species disappears after a shock, plants and animals higher up the chain can lose their food or breeding partners and collapse in a domino effect. Classic examples in nature show how removing one top predator can lead to overgrowth of some plants and loss of others. A big environmental jolt from a passing black hole could do similar damage, but on a global scale. Small, isolated populations are especially at risk because they can't get new members from elsewhere. Their limited genetic mix makes them less able to adapt to new conditions, so recovery is less likely without human help. Ecosystem resilience, the ability of nature to bounce back, depends on several practical things. Diversity is the clearest buffer. A forest with many tree species is more likely to keep some trees alive if a disease or drought hits. Connectivity helps too. Wildlife corridors let animals move to safer areas when local conditions become hostile. Safe spots, called refugia, are places where local conditions remain livable and can act as launch points for later recovery. Mountain valleys, deep ocean trenches, or underground aquifers can play that role. Redundancy matters. If multiple species perform similar jobs, several pollinator species, for instance, the loss of one is less catastrophic. Examples from everyday life include seed banks and soil seed banks that preserve plant diversity underground, and microbial communities in soil that help rebuild nutrients after a fire. Human actions can boost resilience, restoring wetlands, creating migration corridors, captive breeding programs, and saving genetic material, but these are more like emergency repairs than instant fixes. Recovery is possible in some cases, but it takes time and depends on how sudden and severe the change was. Slow shifts let species move, adapt, or evolve. Fast, violent shocks leave fewer survivors and break important ecological links that are hard to reassemble. New ecosystems can form after major disturbances, sometimes completely different from what existed before, and those can support life, just not the same life. Practical steps that increase the odds of survival include protecting a wide range of habitats now, keeping population sizes healthy, and maintaining genetic diversity so species have options. In short, resilience is not magic, it's more like a well-stocked toolbox. And unlike inviting a black hole over for tea, investing in biodiversity is something humans can actually do without needing a cosmic invitation. Infrastructure failure modes and human vulnerability. A very close pass by a compact massive object would create strong differences in gravity across the planet, and those differences translate into ground shaking, ocean surges, and shifts in the crust. In plain terms, parts of the Earth could be tugged harder than others, like stretching a rubber band unevenly. That stretching can crack roads, tilt buildings, and overload bridges. Think of the way freezing and thawing makes potholes appear, but on a much larger and faster scale. Electric substations are particularly fragile. Transformers are heavy, delicate, and picky about being jolted out of alignment, so violent shaking or sudden flooding can knock them out and put entire regions in the dark. Power loss cascades quickly into other failures. When high-voltage lines or a handful of key transformers fail, homes lose heat or air conditioning, traffic lights stop, and fuel pumps can't operate, leaving people stranded and intersections chaotic. Hospitals often have backup generators, but those are designed for hours or days, not indefinite outages compounded by blocked roads that prevent fuel deliveries. A real-life example, a neighborhood elevator getting stuck during a blackout traps residents, and if the building's elevators are out and stairwells are blocked, elderly or disabled people are the ones who can't get out. This is not theoretical, it's practical and immediate. Communications and satellites are another fragile layer. If satellites are nudged out of their precise orbits or damaged, GPS signals and long-distance phone and internet routing can falter. Many banking systems and telecom networks depend on satellite timing and positioning, so a disruption can mess with transaction clearing and mobile networks. On the ground, cell towers need power and undamaged backhaul cables. Without them, first responders lose coordination and families can't check on each other, so that precious, first MOK, text may never be sent. It's like losing the town's busiest phone booth right when everyone needs it, only it's the whole town and the booth runs on software. Water and sanitation systems show fragility that quickly affects health. Municipal pumps and treatment facilities require steady electricity and intact pipelines. When pumps stop, pressure drops, contaminants can backflow, and sewage systems can overflow. A useful everyday comparison is a home sump pump failing during a storm. Water pools and damage accelerates. Now multiply that by thousands of homes and the damage adds up fast. Food supply chains suffer too. Trucks can't move on damaged roads, refrigerated storage loses power, and fresh produce spoils, leaving grocery shelves bare and people forced to rely on non-perishables. Human vulnerability is magnified by social and physical inequalities. People without savings, those living in high-rise apartments without personal transportation, and those who require electrical medical devices at home are at far greater risk. Community examples are instructive. Neighborhoods with strong local networks share generators, water, and skills, while isolated residents may be overlooked. Stress, uncertainty, and rumors can also erode social order. Looting and opportunistic crime sometimes arise when essential goods disappear, and mental health impacts mount, kind of like how a flu hits a household hard when no one can agree on who should fetch the chicken soup, but on a societal scale. Finally, many failure modes are linked even when they look separate. A severed highway makes fuel delivery impossible, which keeps generators idle, which prevents water treatment, which creates disease risk. One broken link can topple a chain. Small, everyday practices can blunt some of that. Having cash on hand, spare batteries, and a simple hand crank radio helps. And while humor is precious in dark times, your smart fridge might judge your snack choices, but it won't fix a down transformer. Practical planning and community-level redundancy are what actually reduce the most dangerous human vulnerabilities. Detection: how we would spot an approaching black hole. Astronomers would first spot something odd by watching motion. Stars and planets have predictable paths, and when a massive dark object drifts nearby, those paths get nudged. The nudge could show up as a tiny change in a star's position across the sky, or as an unexplained wobble in the motion of an outer planet or a spacecraft. Think of it like watching birds flying in formation. If one bird suddenly changes course because a kite drifted into the group, the break in the pattern is what draws your eye. Surveys that scan the sky, looking at millions of stars night after night, are key to catching that break. These projects measure where stars sit on the sky very precisely. If a compact dark object passes between us and a distant star, it can act like a small magnifying glass and briefly brighten the background star. That brightening, called microlensing, does not depend on the intruder giving off light, it only depends on gravity bending light. Wide-field telescopes that monitor the sky for transient flickers are essentially on the lookout for such magnifying glass events, and they can flag candidates for follow-up with sharper instruments. If the passing object is collecting gas or dust as it moves, it will heat that material and light up, often in high-energy light like 10th rays or in radio waves. Telescopes tuned to those wavelengths would see a new glowing source where nothing was before. This is a lot like spotting a car that suddenly turns on its headlights in a dark field. Even if the car itself is hard to see, the light it makes is obvious. Multiple observatories can compare notes, optical teams find a candidate, 10th ray teams check for hot gas, and radio arrays look for jets or steady emissions. Coincidence strengthens the case. Precise clocks help too. Pulsars, spinning neutron stars that send out regular radio pulses, tick with remarkable steadiness, and a nearby massive object would slightly change the arrival times of those ticks. That change is a subtle shift, like the way a nearby truck rumbling past can make a building creak at a slightly different rhythm. Networks that monitor pulsars can pick up correlated timing shifts that point to a gravitational disturbance somewhere in the sky. Similarly, the tracking of spacecraft and the constant ranging of satellites reveal tiny deviations in motion. If probes at the edges of the solar system begin to drift off their predicted routes, investigators sit up and pay attention. No single method would work alone, confirmation comes from different techniques agreeing. A microlensing event followed by a new 10th ray source and simultaneous wobbling in nearby stars would paint a consistent picture. Observatories already share alerts and data quickly, so suspicious signals get checked fast. In short, even a dark, silent interloper would leave fingerprints, bending light, perturbing orbits, lighting up captured gas, and tugging at precise clocks. And while it might sound like science fiction, the way we watch the sky is a lot like neighborhood vigilance: many eyes, many cameras, and the habit of noticing when something out of place shows up. Warning timescales: hours, years, or centuries. Whether Earth would get a heads-up depends mostly on how close and how fast the black hole is moving relative to us. If it is far away and moving slowly through the outermost parts of our system, its first effects would be tiny nudges to distant icy bodies. If it is already barreling toward the inner system, those nudges turn into visible motions of planets and sudden changes in tides. In practical terms, some encounters would announce themselves very early, others barely at all. Think of it like two ways to notice a friend: either you see them walking toward you from a block away, or they jump out from behind a bush. A truly close approach gives almost no warning. A dark, compact object that comes near enough to tug at Earth's orbit or the oceans will produce rapidly growing forces. Earthquakes, strong tides, and orbital shifts could appear on short notice. These are things astronomers could only detect once the effects are large. By then the clock is short. Because an isolated black hole often gives off no light, we can't rely on a sudden flash to alert us. That's why a very near pass can feel like a blackout surprise: bad for schedule planners, worse for emergency meetings. If the intruder is farther off, astronomers have better chances. Precise tracking of star positions and motions can reveal the subtle pull of an unseen mass well before it reaches us. In addition, light from background stars can bend slightly when a massive object passes in front of them, creating a telltale brightening or shift. This bending acts like a natural magnifying glass. Those methods can give years of warning in many cases, enough time to plan evacuations of low-lying coasts, adjust satellites, or move key infrastructure. It's similar to spotting a slowly approaching storm on your weather app and moving your picnic under a roof. The longest kind of warning comes from disturbances at the fringes of the solar system. A passing massive object can jiggle the far-out reservoir of icy bodies, sending some of them onto long inward journeys. Because those outer objects move on enormous, slow paths, the consequences take a very long time to arrive at the inner system. That's like tapping one end of a long line of dominoes and waiting for the last one. The initial shove is quick, but the impact at your feet happens late. In those scenarios, humanity could have decades or centuries to respond, which is plenty to build defenses, move critical assets, and maybe stockpile extra coffee. Realistic preparation depends on which warning regime we're in. Short warnings require immediate, local responses, fast evacuations, emergency power and communication. Medium-term warnings allow for moving satellites out of harm's way and protecting coastal cities. Long warnings mean sweeping planetary planning and international coordination. And while it sounds dramatic, most detection methods today favor giving us at least some advance notice in many plausible situations. Only a very sudden, extremely close object would leave almost no time at all. In short, sometimes you'd have just enough time to grab your phone, and sometimes you'd have enough time to plan a very elaborate, very slow-motion emergency drill. Evacuation, mitigation, and feasible responses. A passing black hole would change the gravity around Earth in ways that depend on how close and how heavy it is, and those effects can be noticed in advance if astronomers catch the disturbance early. Telescopes and detectors can see stars wobble, gas heat up and glow, or subtle ripples in space that announce something big is passing by. Early warning gives time to act. Detection is the golden window. Act too late and options narrow quickly. Full planetary evacuation is not a practical option. We currently cannot lift more than a tiny fraction of Earth's population into space at once. Rockets and habitats are built for explorers, not cities. Instead, evacuation plans would need to be local and targeted, move people away from coastal zones if strong tides are expected, relocate residents from landslide-prone slopes if seismic shaking is forecast, and clear low-lying areas if major ocean sloshing is predicted. Think of it like a hurricane plan on steroids, same basic idea, far harder to pull off. A short-term example people understand is how cities clear subways and shorelines before a major storm. We would do that, but on a faster and more coordinated global scale. Directly changing Earth's path to dodge a black hole is effectively impossible with our current technology. We can't push the whole planet like a car. So mitigation focuses on protecting what we can, stabilize power grids, harden data centers, safely shut down nuclear plants if they are at risk, and secure satellites that guide communication and navigation. Practical measures include moving seed banks and critical backups to multiple, well-protected sites, and ensuring hospitals have independent power and supplies. Simple everyday steps scale up. The same way people bolt furniture to avoid earthquake injuries, nations can reinforce key infrastructure to reduce systemic collapse. Coordination and preparedness become the most feasible responses. International emergency protocols, clear chains of command, and pre-stocked supplies should be ready to deploy where needed. Space agencies already monitor many cosmic threats. Expanding those networks to share real-time alerts would buy time. Training exercises that simulate rapid, gravity-driven disruptions would help authorities avoid paralysis. Small, concrete examples: maintaining multiple, geographically separated backups of financial and scientific records, rotating emergency food reserves, and keeping mobile medical teams primed for rapid deployment. A little humor helps morale. Better to have a decade-old council meeting about canned beans than a panicked argument when the shelves are bare. Long-term investments improve resilience even if they won't let us flee. Building more robust launch capacity, for instance, gradually increases our ability to move people and hardware into space for refuge or research, though it remains far from a global evacuation solution. Expanding underground and climate-resilient shelters, improving early warning science, and diversifying food and energy sources all reduce vulnerability. Community-level preparedness, like local emergency plans, backup generators at hospitals, and clear evacuation routes, is often more effective than grand, last-minute ideas. In short, early detection, practical local evacuations where needed, hardening critical systems, and strong international coordination are the realistic responses. Hope and a sense of humor help, but planning and preparation are what really stand between a surprised planet and a workable outcome. Historical simulations and notable case studies. Early computational models treated a passing black hole much like a heavy bowling ball rolling past a set of lighter balls, using straightforward gravity equations to track who gets nudged and who stays put. These n-body simulations, which follow many point-like objects interacting under gravity, were the backbone of the first hands-on studies. They were used to test whether a wandering compact object could fling planets out of their orbits or send a rain of comets toward the inner system. In plain terms, run a virtual solar system, drop in a heavy visitor, and watch how the celestial billiard table responds. As methods improved, researchers moved from simple point mass experiments to richer, more realistic approaches. Smooth particle hydrodynamics, or SPH, treats gas and stars like lots of tiny fluid particles, so when a star gets pulled apart by a black hole, the simulation shows how the stellar material stretches, heats, and sometimes lights up. Think of it like modeling a water balloon being pulled. The balloon stretches and sprays water in streams, and that's roughly how a star behaves when tides tear it apart. Those SPH runs are the ones that produced convincing virtual versions of tidal disruption events, the bright flares astronomers actually see when a star is shredded near a big black hole. Other notable case studies come from work on the distant debris belt around our system, the Oort cloud. Scientists used Monte Carlo and N-body techniques to simulate what happens when a compact object passes through that distant swarm of icy bodies. The common conclusion is practical and a little boring. Small nudges to many comets can add up, increasing the number of long-period comets sent inward over long timescales. In everyday language, it's like jostling a bookshelf slightly. Books might tumble months later. The immediate effect at Earth's orbit is usually minor unless the encounter is unusually close. Studies focused on encounters with binary star systems also revealed striking outcomes. When a black hole interacts with a tight stellar pair, one star can be captured while the other gets flung away at high speed. This process, known in the literature and used to explain fast-moving stars, highlights how encounters can rearrange bodies without destroying whole planets. A neat life analogy: one friend gets dragged into a new social circle and the other bolts out of the party humming a new tune. Finally, teams running full relativistic simulations tackled the extreme cases: what happens when the black hole's gravity is so strong that Newton's rules aren't enough. These numerical relativity runs are computationally heavy but essential to model close encounters where spacetime itself gets noticeably curved. Results from these simulations underline a simple practical message: for Earth to face catastrophic direct effects, the visitor must come extremely close. Otherwise, most notable impacts are indirect: comet showers, changes to outer belts, or the occasional star getting ripped into a luminous flare, interesting to astronomers, inconvenient to planetary defense planners, and a great plotline for science fiction writers. Numerical modeling techniques for flybys. Scientists build flyby models by turning space into something a computer can understand, either a swarm of little pieces that feel gravity, or a mesh of boxes that hold values like density and speed. Particle methods treat objects as many interacting dots, which is handy when you want to follow debris or individual chunks of matter. Think of it like tracking individual grains of sand in a sandbox. Grid methods, by contrast, divide space into cells, like pixels in a picture, and compute how things flow from one cell to the next, which works well for fluids or gas around an object. Hybrid approaches mix both, because sometimes you need the detail of particles near a planet and the smoothness of a grid farther away. It's practical and flexible, like using a zoom lens for close-ups and a wide angle for the rest. To move things forward in time, models use time stepping, which is basically taking tiny leaps from one moment to the next. Small steps catch fast changes but take longer on a computer. Some stepping schemes are designed to conserve quantities like energy or momentum so the simulation doesn't drift into nonsense over time. That matters when a black hole swings by, because little errors can add up and give you results that are as believable as a magic trick. Adaptive time stepping helps by taking tiny steps during dramatic close approaches and larger ones when things are calm, like slowing down to tie your shoe on a busy sidewalk and jogging when the coast is clear. When gravity gets strong, simple recipes don't cut it and the models need to include corrections from Einstein's picture of gravity. Full solutions of Einstein's equations are complicated, so modelers often use approximations when possible, or solve the full equations on a grid when they really must. Think of it as choosing between a rough sketch and a full painting. To get fine detail where it matters, many codes use adaptive mesh refinement. The computer adds smaller cells in regions of interest, much like zooming in on a photo to sharpen a face while leaving the background softer. This saves computing time, though it still demands lots of processors working together, like an army of chefs all following one complicated recipe. Earth and any nearby material need different treatments within the same simulation, because solid bodies and gases behave differently. Engineers and scientists model a planet's solid parts as a network that resists stretching. Picture a bowl of jello held in a mesh of rubber bands, while the atmosphere and any surrounding gas are handled as fluids that can flow and slosh. Coupling those approaches is tricky. The model must handle contact and energy exchange at the surface, and it must do so without letting numerical artifacts, fake wiggles from the calculator, take over. Sensitivity tests are common, where you nudge an input a bit and watch the outcome. Chaotic systems can react like a double pendulum, so ensembles of runs help show likely ranges rather than a single, possibly misleading answer. Finally, any model is only as useful as its checks and visualizations. Benchmark problems, simpler scenarios with known behavior, are used to validate codes, while visual output turns raw numbers into movies and maps that humans can interpret. Parameter studies sweep through different assumptions to reveal which factors matter most, much like trying different spice levels to find the best flavor. Observational data, when available, anchors the models and limits wild speculation. Without that, simulations are clever guesses. And yes, they keep getting better as algorithms and computers improve, so the simulations are less of a crystal ball and more of a finely tuned microscope. What observatories would observe? Light and gravity. A black hole passing near Earth would speak in two languages, light and gravity. Telescopes would first notice unusual changes in brightness and position of stars. As the black hole moves between us and a background star, it can act like a giant, invisible magnifying glass, briefly making that star look brighter or even producing multiple, distorted images. Think of holding a magnifying glass over a newspaper, letters get bigger and warped. Sky surveys that watch large areas at once would be the ones to catch those sudden brightening events. Different kinds of light would tell different parts of the story. If the black hole sweeps through clouds of gas or dust, that material gets stirred and heated gas glows at high energies. 10th ray and gamma ray telescopes would see hot, compact flashes where gas is being pulled in and ripped apart. Radio telescopes, on the other hand, are good at spotting long, narrow signals, jets of energized particles that can shoot away from the vicinity of a black hole like cosmic fire hoses. Optical and infrared instruments would trace how stars wobble or shift position in the sky as the black hole tugs on them. In everyday terms, it's like checking a crime scene with different tools. A flashlight shows you the room, a metal detector finds hidden coins, and a thermal camera finds where the heater is leaking heat. Gravity detectors would add a very different, and very direct, clue. These instruments listen for tiny ripples in the fabric of space itself, ripples created when massive objects move fast and accelerate. Picture dropping a stone into a calm pond and watching the surface ripple outward. Gravity detectors look for the analogous ripple in space. Ground-based networks of detectors compare signals across thousands of kilometers to recognize a real ripple and to estimate where it came from on the sky. If the passing object is massive and close enough, the detectors would record a distinctive chirp or sweep as the gravity disturbance passes by. Light and gravity signals don't always arrive in the same way. The gravity ripples come from the motion of mass directly, so they can be produced right away as the black hole moves. Light, however, often depends on gas being heated or stars being disturbed, which can take time to develop and sometimes produces signals that peak later or more slowly. Like hearing thunder after seeing lightning, you might see a flash of high-energy light or hear a radio burst after the gravity signal has already gone through, or sometimes you might get a bright optical flare with no strong gravity ripple at all if there isn't much mass moving quickly. Putting together these observations is the trick. A sudden brightening in optical surveys might be microlensing caused by a passing compact object, but similar brightening can come from exploding stars or variable stars, so follow-up with 10th ray and radio telescopes helps confirm the picture. Meanwhile, a gravity detector registering a ripple will send alerts to telescopes to look in the right patch of sky. The challenge is that gravity detectors can point only roughly, like knowing a sound came from somewhere across a fairground but not exactly which booth. Telescopes then have to scan wide areas quickly to catch any transient light. Coordinated observing, rapid alerts, and a bit of luck are the practical tools astronomers would use to turn those faint, strange signals into a confident detection of a passing black hole. Lessons from disrupted exoplanetary systems. Astronomers have actually watched planetary systems get shaken apart, and those observations tell us a lot about what a close gravitational intruder, like a passing black hole, might do. Some stars show dusty tails where small planets are literally evaporating as they skim too close to their star, which is a clear sign that violent forces can shred solid worlds. Others are surrounded by belts of rock and dust that look like someone swept the floor messily after a collision, meaning collisions and scattering events are common in disturbed systems. These patterns come from real observations. A handful of stars show disintegrating planet fragments transiting in front of the star. White dwarf stars often contain traces of rock in their atmospheres, proof that larger bodies were broken up and fell in, and freely wandering planets have been detected by the way their gravity briefly magnifies background starlight. Such examples teach that the outcome of a strong perturbation depends heavily on the system's layout. If a system has one or more massive planets sitting out in the middle, they can act like traffic cops, redirecting or absorbing incoming objects and sometimes protecting inner worlds. But those same giant planets can also amplify chaos. If they get knocked out of place, they fling smaller planets around like bowling pins. Picture a roller rink pileup where a big guy trips and sends everyone flying. Short sentence. The exact balance depends on how tightly packed the planets are and how massive the movers are. Debris behavior in observed systems gives a practical warning. A passing heavy object tends to stir up comets and asteroids, increasing the rate at which rocky bodies fall inward. We see analogues of this in systems with warped or clumpy debris disks, where the material's new orbits lead to more collisions and inward drifts. That extra drizzle of rocks and dust can darken a planet's sky temporarily or, in extreme cases, batter a world with impacts. Think of it as shuffling a deck where suddenly more cards are pointed at the face of the house, messy, and potentially costly. Another lesson is about survivability of individual planets. In several observed cases, inner rocky bodies can survive massive upheavals if they avoid close approaches to the disturbing mass and to other giant planets. Survivors often end up on more eccentric, oval-shaped, or tilted orbits, though, which changes climate stability. Short sentence. We've seen exoplanets on wildly eccentric paths and planets around dead stars that are likely remnants of a formerly richer system. These are real-world examples that violent events don't always mean complete annihilation. Finally, disrupted systems teach a caution about predictability. Outcomes are sensitive to small differences. A slightly different timing or angle of an encounter can mean the difference between gentle orbital nudging and catastrophic ejection. Observational evidence of scattered planets, misaligned orbits, and polluted stellar atmospheres shows a broad range of possible end states. So while dramatics make good sci-fi, the scientific takeaway is nuanced. Sometimes a planet can survive a close call, sometimes it becomes interstellar debris, and sometimes it ends up in a new, awkward orbit. A little like surviving a surprise party where the surprise is being thrown into the neighbor's yard. Separating myth from science fiction. A black hole is simply a region where a lot of mass is squeezed into a very small space, so gravity near it becomes extremely strong. That does not mean it acts like a cosmic vacuum cleaner roaming the galaxy and sucking up everything in sight. Gravity behaves the same way no matter what object produces it. What matters is how much mass there is and how far away you are from it. For example, if the Sun were suddenly replaced by a black hole that had the same mass, Earth would keep orbiting the same way, but night would be permanent and life would get very cold. That helps separate dramatic images from real physics. Stories about whole planets being instantly swallowed from across the sky come from mixing up close encounters with distant ones. When a heavy object passes very near another body, the stronger gravity on the nearer side can pull harder than on the far side. This difference is what would stretch or tear things apart. Call it a tidal pull, like when a strong tug on one end of a blanket rips it away from the other end. A light everyday example is standing near a passing truck and feeling a gust that rattles the windows. A close black hole would be the cosmic equivalent of that gust, but far more destructive if it were close enough. However, to actually pull Earth apart or capture it, the black hole would have to come extremely close, much closer than the neat, dramatic pictures in movies. Close passes can make trouble in realistic ways that are less cinematic but more relevant. A nearby heavy object could change Earth's path around the Sun, throwing seasons and climate into chaos, or it could strip away part of our atmosphere. Materials sitting around the black hole, dust, gas, or even pieces of a planet, can heat up and glow very brightly, often in high-energy light that telescopes detect as a flare. Astronomers watch for those bright signatures when they look for real interactions, so they don't rely on hearsay. In short, the real dangers are shifts in orbit and loss of atmosphere, not a graceful spiral into a black hole like a movie death scene. Finally, the bottom-line reality is comforting. A random black hole drifting through our neighborhood is not a likely threat. Space is mostly empty, and objects have to come very close to cause catastrophic effects that make such encounters exceedingly unlikely. You can think of it as standing in a huge parking lot. The odds of a car driving straight through your small patch of asphalt are tiny, even though cars exist. So while the science behind black holes is fascinating and real, most of the terrifying scenarios belong squarely to science fiction rather than everyday risk. Edge cases, plausible but extreme scenarios. A close pass by a black hole would change things mostly by gravity tugging on masses and by the way that tug changes across distance. How strong the effects are depends on how heavy the black hole is and how close it comes. Tidal forces are the key idea here, that is the difference in pull between one side of Earth and the other, and you can think of it like a tug-of-war where one side of a blanket is yanked harder than the other. The Moon already makes tides by pulling on Earth's oceans, but a passing compact object could make those differences far larger, stretching the planet and its seas unevenly. That stretching can pump energy into the ground and oceans, and that energy can show up as bigger tides, increased earthquakes, and shifts in ocean circulation. In short, weather and geology could get a rude nudge. If the black hole gets very close, the gradient in gravity across Earth becomes extreme and pieces held together by their own gravity or material strength can come apart. This is the same mechanism behind tidal breakup. When the pull from the visitor overwhelms the pull holding something together, it falls apart. Picture pulling a tablecloth fast from under a set of dishes. If pulled gently the dishes slide, but if yanked hard some might tip or fall. For a planet, that could mean atmospheric loss or large-scale structural failure in the crust where stresses concentrate. Though fall apart is not usually instantaneous, effects can build up over hours to years depending on the encounter. A different and subtler route to trouble is through stirring the solar system's reservoirs of small bodies. A pass through the outer regions would perturb comets and asteroids that normally sit far away and calm, nudging some onto paths that cross Earth's orbit. Think of a bowling ball rolling through a cloud of ping-pong balls. A lot of harmless drift suddenly becomes a scatter of fast-moving pieces. Those newly sent-in comets could increase impact risk for a long time after the encounter, creating a comet shower that persists for decades or centuries as the scattered population relaxes back into a new configuration. A direct intersection with Earth is a dramatic image, but the reality is odd and counterintuitive. Many black holes, even very heavy ones, are physically tiny in size compared with Earth, so their hole part is extremely compact. Passing right through would concentrate effects along a narrow track and send seismic waves outward, like dropping a very heavy pebble through a jelly layer and watching ripples spread. That could be locally catastrophic along the track, but it wouldn't shred the whole planet like a cookie cutter. The visitor's gravity would still be strong enough near its path to fling debris and heat things up, though, so small in size does not mean harmless. Capture into orbit is another plausible extreme. If the passing object loses enough energy, it could be trapped by the Sun or even become gravitationally bound to Earth, turning the solar system into a three-body dance that can become chaotic. Orbital capture can change planetary orbits slowly but seriously, altering insolation patterns and climates over long stretches. For a practical analogy, imagine adding a heavy, unmarked ball to a cluster of spinning playground carousel riders. The motion adjusts, people slide, and things that were once predictable become messy and less safe. We would likely get warning signs before the worst outcomes. Modern astronomical surveys, observations of stellar motions, and instruments that detect ripples in spacetime are sensitive to compact objects moving through space, and a significantly close intruder would alter surrounding stars or create detectable lensing of light. That's a bit like weather radar picking up the leading edge of a storm before it hits land. Planners could at least anticipate elevated comet risk or tidal anomalies and prepare for the secondary effects, such as coastal flooding or increased seismic monitoring. In short, a black hole passing by could strain oceans and rock, scatter cometary messengers toward Earth, and, in rare capture or very close pass cases, rework orbits and climates, but the precise outcome hinges on mass, speed, and distance. Practical defenses are limited to observation and preparedness rather than stopping gravity itself, so the best human response is to keep our telescopes, monitoring networks, and disaster plans tuned up. And no, a quick trip to the beach for a front-row view is not recommended. Global cooperation and planetary defense planning. Early warning networks already used for tracking dangerous space objects offer a ready model for planning how the planet could respond to an approaching black hole. Organizations such as the International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAG, together with national space agencies like NASA, ESA, and JAXA, show how telescopes, orbiting sensors and data centers can share observations quickly. Think of it as a global constellation of smoke detectors that call the fire brigade the instant anything odd shows up in the sky. That kind of constant scanning and rapid alerting would be essential if gravity from a passing compact object started changing satellite orbits or sea levels. Clear decision rules and a trusted command structure are the backbone of any effective planetary defense. Nations must agree ahead of time who speaks for the planet when seconds count, and what choices are allowed when many lives are at stake. Practical examples from everyday life help. Air traffic control coordinates hundreds of planes without arguing about who owns the sky, and emergency managers run joint hurricane drills between states so shelters, supplies, and road closures are ready to go. In the same way, an international protocol would spell out who activates evacuation plans, who reroutes satellites, and how military and civilian assets are used without last-minute diplomatic confusion. Short chains of command reduce delay, and rehearsed plans reduce panic. Pooling technical resources across borders is another key piece. No single country owns all the telescopes, supercomputers, or launch vehicles needed for a fast response, so sharing is the name of the game. Scientists in different time zones can hand off analysis like relay runners, and ground stations around the globe can keep continuous contact with critical spacecraft. This is similar to how streaming services use distributed servers to avoid outages. If one node goes down, others pick up the load. Regular multinational simulations and tabletop exercises, practical, live drills where agencies run through realistic scenarios, train people to act together, not at cross purposes. Logistics matter too. Spare parts for satellites, portable power units, and redundancy in communication networks are the nuts and bolts items that keep a global plan from collapsing. Public communication and fairness must not be afterthoughts. Transparent, calm messaging prevents rumors and panic, and plans that consider the needs of poorer or more remote communities keep responses humane. Lessons from large-scale vaccine rollouts and disaster relief show that coordinating shipping, cold storage, local health services, and trusted community leaders makes aid actually reach people who need it. Legal and diplomatic frameworks, facilitated through the United Nations and existing space governance offices, can set rules for resource sharing, data access, and liability, so countries know their obligations and rights ahead of crisis. Humor helps, too. Treating Earth's defense like an international potluck, everyone brings one thing they do well, keeps morale up while we figure out who's bringing the giant shovel to move planets, metaphorically speaking. In short, a practical plan rests on shared sensors and data, pre-agreed decision processes, pooled technical and logistical resources, and clear, fair communication with the public. Cooperation is not optional. Dealing with a global gravitational threat would be a team sport, and the better the teamwork during peacetime, the more likely humanity will act smoothly if a rare, serious test ever arrives. Public communication and avoiding panic. People respond best when officials speak plainly about what is known, what is not known, and what steps are being taken. Start messages with clear facts. For example, if scientists can say a passing dense object will not cross Earth's path, say that plainly. Use short, direct sentences to announce immediate actions. Then follow with a slightly longer explanation that uses simple language, like explaining gravity as the pull that keeps our feet on the ground, so people can connect unfamiliar ideas to daily experience. Trustworthy messengers matter. A calm scientist or local emergency manager shown on camera, speaking with empathy, does more to steady people than a flurry of anonymous posts. Use familiar examples to make points. Treat a public update like a routine weather alert or a traffic advisory, brief, specific, and telling people exactly what to do. Mix long reassurance lines with quick practical tips. This avoids sounding robotic while still giving clear instructions. Address uncertainty out loud. Say something like, "Here's what we know now," and then, "Here's what we are still checking." Short reminders help. Check official channels, do not forward rumors, and follow local guidance. People fear the unknown, and quiet gaps in information are quickly filled by speculation. Filling those gaps early, with simple Q&A bullets that answer likely questions, keeps the chatter down. Humor can help, carefully used. A quick line like, "No need to hoard canned beans unless told otherwise," can lighten the mood while reminding people not to overreact. Coordinate every message across agencies and platforms so people get the same answer whether they watch TV, scroll social media, or hear a siren. Have a single hub for updates, a website and verified social accounts, and teach people how to find them. Use visuals when possible, such as clear maps or simple diagrams that show what is happening and what it means for neighborhoods. Visuals are faster to understand than long paragraphs. Prepare spokespeople ahead of time and rehearse likely questions. Regular training keeps messages consistent and reduces off-the-cuff statements that cause confusion. Also set up hotlines and community centers for people who need reassurance or help, because a personal voice on the phone often calms anxiety more than a posted bulletin. Finally, monitor social media to correct false claims quickly, and empower community leaders, teachers, religious leaders, neighborhood organizers, to spread calm, practical guidance. These combined steps make panic much less likely and help communities act sensibly. Final scientific assessment: could Earth survive a passing black hole? Most black holes come in different sizes, and their danger to Earth depends on how heavy they are and how close they get. A black hole's gravity is what matters, not some spooky vacuum cleaner effect. If it's far away, its pull is weak, just like the moon's pull affects our tides but does not fling us into space. For people who prefer visual anchors, think of the sun and the planets as a calm carousel. A distant heavy rider might wobble the platform a bit, but the carousel keeps turning. Close passes are a different story, because gravity grows quickly as you get nearer. If a black hole were to cruise through our neighborhood close enough to matter, the most immediate risk would be tidal forces, differences in gravity between one side of Earth and the other. Those differences can stretch and compress things. It's the same basic effect that makes ocean tides, only much stronger near a compact heavy object. Picture holding a rubber band near a vacuum cleaner hose. The side closer to the hose gets yanked harder. On a planet that can mean earthquakes, massive ocean sloshing, and in extreme cases the atmosphere being stripped away. Short version: close and fast equals trouble. A more direct danger is orbital disruption. Earth's path around the Sun is a delicate balance between forward motion and the Sun's pull. A rogue black hole that passes near enough could shove Earth onto a different path or even eject it from the solar system. That's not a Hollywood explosion, it's a slow-motion change that would alter seasons and climate over time. However, for a passing black hole to do that, it would have to be very near compared with typical interstellar distances. If it stayed far away, say, well beyond the outer planets, the gravitational tug would be marginal and our orbit would be essentially unaffected. Think of a large truck driving down your street versus a freight train far off in the distance. One rattles your windows, the other you barely notice. Detectability and practical outcomes work in our favor. Astronomers survey the sky and track the motions of stars and gas, and a massive object moving through space usually gives off clues. Nearby gas heats up and can glow in 10th rays, or stars get nudged and reveal a new gravitational influence. We would not be completely blind to a black hole on a close approach. That said, detecting an unlit, quiet black hole well before it crosses into dangerous distance is challenging, but not impossible if it interacts with gas or stars. So while a sudden, undetectable strike is the stuff of movies, the real universe tends to leave fingerprints we can follow. In the final balance, Earth can survive a passing black hole unless the encounter is exceptionally close. Distant encounters produce minor nudges and tides, and life goes on. Extremely close encounters can be catastrophic, stripping atmosphere, changing orbits, or even pulling material away, but those scenarios require near collisions that are astronomically unlikely. Practically speaking, the sky watchers would probably spot warning signs and scientists would model the trajectory. Prepare for headline writers and dramatic music, but from a strictly scientific view, our planet is not doomed by the idea of a random faraway black hole passing by. So could Earth survive a passing black hole? Short answer, almost certainly, and here's why, in plain talk. A black hole is just an object with a huge amount of gravity packed into a very small space, like a bowling ball with the weight of a mountain. If it stays far away, its pull is like feeling a truck rumble past your house, noticeable only if it's close. For a black hole to tear Earth apart or swallow us, it would have to come so close you'd spot it in the sky, closer than the moon, and the odds of that happening are vanishingly tiny. If a small one did pass at a safe distance, we might feel a tiny change in Earth's orbit, like someone nudging your chair, or see stars wobble in ways astronomers could detect well before disaster. Big, dramatic effects need a close encounter, and we're not on any cosmic collision course right now. Astronomers watch the skies constantly, so a wandering beast would not stay hidden for long. Thanks for sticking with me through the wild physics, scary sounding, but mostly safe for real life. If you enjoyed this, hit like, subscribe, and tell me in the comments what cosmic, what if, you want next: rogue planets, neutron stars, or what would happen if the sun took a coffee break. Next up, we'll explore how rogue planets wander the galaxy and how we'd spot one headed our way. Stay curious, keep looking up, and try not to panic about hypothetical bowling balls from space. They don't RSVP.